Hello there, and welcome where curiosity settles in comfortably and science is explored in a calm, unhurried way that hopefully lets your mind relax while still giving it something interesting to hold on to. Tonight, the focus drifts toward a place most people will never see, a place that exists right here on Earth, yet still manages to unsettle even experienced scientists. It is called the Galathea Deep, and despite decades of research, advanced submersibles, and detailed mapping technologies, it remains one of the least understood environments on the planet. The name might sound almost elegant at first, perhaps even historical or academic, but what it refers to is anything but gentle. It is the deepest known point of the Philippine Trench, far beneath the surface of the Western Pacific Ocean. Down there, sunlight never arrives, temperatures hover just above freezing, and the pressure is so intense that ordinary materials collapse quickly unless they are engineered specifically to survive. That alone would be enough to make it scientifically interesting, yet what truly keeps researchers returning is the long list of unanswered questions. Every expedition seems to confirm how much still isn't known. Before settling further into this quiet exploration, there is something I always enjoy asking because it makes these conversations feel a little more shared, even though we are scattered across different places and schedules. Where are you listening from tonight? And what time does it happen to be in your part of the world? It is a simple detail, yet it creates a subtle connection. Some listeners are just starting their day, others are winding down, and a few are probably somewhere in between, using a calm science discussion as a small pause in an otherwise busy routine. If you find this kind of slow, thoughtful exploration helpful for relaxing, focusing, or simply drifting off to sleep, a like or subscription helps this space reach more people who appreciate quiet science conversations. There is never any rush or pressure about that, just a small note in case you feel the content is worth keeping around. Now, when most people think about mysterious environments, the mind usually jumps outward towards space. Distant planets, black holes, and galaxies tend to dominate popular imagination. It makes sense because space is vast, visually striking, and often portrayed dramatically. Yet oceans, especially the deeper sections of them, remain far less explored than the surface of the Moon or Mars. That fact surprises many people when they first hear it, but the technical challenges involved in deep ocean exploration are very real. Crushing pressure, limited communication capability, darkness, and extreme isolation combine into conditions that are difficult to replicate and even harder to work within for extended periods. The Galathea Deep fits squarely into that category of environments where access is possible but never simple. Researchers do not casually visit it. Every descent requires extensive preparation, specialized vehicles, and a level of risk assessment that goes well beyond typical marine studies. Even with modern robotics and reinforced submersibles, missions remain expensive, complex, and relatively rare. Each trip is planned carefully because there is always the possibility that equipment will fail or unexpected conditions will appear. Part of what unsettles scientists is not danger in the dramatic cinematic sense, but uncertainty. Scientific work depends heavily on predictability. Experiments are designed with expected ranges, tolerances, and repeatable conditions. The Galathea Deep resists that predictability. Data collected there sometimes behaves differently from models developed elsewhere. Organisms discovered at those depths occasionally show adaptations that challenge assumptions about how life can function. Geological activity in the region adds another layer of complexity, because the Philippine Trench sits within an active tectonic zone. When discussing deep ocean trenches, numbers alone rarely convey the full picture. Hearing that something is around 10,000 meters deep sounds impressive, but it is difficult to visualize. A commercial airplane cruising at typical altitude would fit comfortably inside that depth with room to spare. Mount Everest, if placed there, would not reach the surface. These comparisons are not used for drama. They simply help translate scale into something more familiar. Another aspect that contributes to the lingering unease is sensory deprivation. Humans rely heavily on vision for orientation and reassurance. At those depths, vision becomes irrelevant without artificial lighting. Even then, the illuminated area remains small, surrounded by vast darkness. Submersible crews often describe a sense of disconnection from ordinary spatial cues. Robotic probes relay video that looks calm and uneventful, yet researchers reviewing that footage understand the extreme environment behind it. There is also the matter of time perception during deep missions. Operations proceed slowly because rapid movement risks equipment damage. Communication delays, careful manoeuvring, and methodical sampling stretch what might otherwise feel like a routine task. Scientists are trained for patience, but extended exposure to such conditions can still produce psychological strain. That factor rarely makes headlines, yet it influences how missions are structured. Interestingly, fear is not quite the right word many researchers use. Respect is more common. Respect for pressure levels, respect for engineering limits, respect for unknown biological and geological factors. Still, when experts repeatedly emphasize respect, it hints at underlying caution. The Galathea Deep has a reputation for reminding people how incomplete current knowledge remains. Historical context adds another dimension. The trench was named after the Danish research vessel Galathea, which conducted deep-sea expeditions in the mid-20th century. At that time, technological capability was far more limited than today. Early measurements were impressive achievements considering the tools available. Subsequent missions refined those measurements and confirmed the trench's remarkable depth. But each new generation of instruments also uncovered new anomalies, unexpected readings, or biological traces that did not align neatly with previous assumptions. That pattern continues today. Sonar mapping has improved resolution dramatically, yet certain areas still produce ambiguous results. Sampling devices occasionally return with material that suggests complex ecosystems, even though conditions seem extremely harsh. Some findings raise straightforward scientific questions. Others prompt broader discussions about how adaptable life can be under pressure, darkness, and minimal nutrient supply. Public fascination sometimes gravitates towards sensational possibilities, but most scientists approach the site with disciplined curiosity rather than speculation. The goal is to understand physical processes, biological adaptation, and geological dynamics. Even so, it is hard to ignore the psychological effect of working at a place that remains largely unseen and poorly understood. Funding agencies also recognize both the importance and the difficulty of these missions. Deep-sea research contributes to climate studies, biodiversity assessments, and geological hazard monitoring. Trenches like the Galathea Deep can influence ocean circulation patterns, carbon storage, and seismic activity. That practical significance ensures continued interest, even though results often emerge slowly. Technology is gradually improving access. Autonomous underwater vehicles can stay submerged longer than crewed vessels. Advanced pressure-resistant materials extend operational depth limits. Imaging systems now capture clearer visuals in low-light conditions. Despite those advances, exploration remains incremental rather than rapid. Every improvement reveals additional complexity instead of tidy answers. Another element that keeps attention focused on the trench is comparison with better-known locations such as the Mariana Trench. While the Mariana system contains the deepest confirmed point on Earth, the Galathea Deep is still among the most extreme marine environments. Differences in geological structure, sediment composition, and biological activity make each trench scientifically distinct. Treating them as interchangeable oversimplifies important nuances. Researchers sometimes describe deep trenches as natural laboratories. Conditions there cannot be recreated easily on the surface, so direct observation provides unique data. Pressure effects on materials, microbial survival strategies, and chemical interactions in cold, dark water all contribute insights relevant to oceanography, astrobiology, and even industrial engineering. At the same time, caution remains constant. Equipment redundancy, emergency protocols, and conservative mission planning reflect the understanding that mistakes at such depths are difficult to correct quickly. Recovery operations can take days or weeks. Weather conditions at the surface also influence scheduling, adding another variable to already complex logistics. For listeners encountering this topic for the first time, it can be surprising how grounded the science remains despite the dramatic setting. Most work involves careful measurement, sample analysis, and incremental theory development. The unsettling aspect comes not from dramatic events but from persistent uncertainty. Every clear answer tends to generate several new questions, and as attention continues to settle on this quiet, distant place beneath the ocean surface, the story naturally begins to widen toward how much of Earth's oceans remain unexplored in general, because understanding that broader context helps explain why a single trench, even one as deep as this, can still hold so many unknowns, which gradually brings us toward the wider picture scientists keep in mind whenever discussions turn to the deepest parts of the sea. If the idea of the Galathea Deep already suggests remoteness, it helps to widen the view slightly and consider the oceans as a whole, because that broader context explains why a single trench can continue drawing scientific attention for so many years. Oceans cover more than 70% of Earth's surface, yet a surprisingly small fraction has been explored in detail. Depending on how exploration is defined, estimates often suggest that over 80% of the ocean floor remains either unmapped at high resolution or completely unobserved by direct human or robotic presence. That number alone tends to reset expectations. Many people assume modern technology has already surveyed most of the planet, yet underwater environments present challenges that make exploration slower than it might appear. One immediate factor is simple physics. Water absorbs light quickly, far more effectively than air. Within the first couple of 100 meters, sunlight fades to the point where visibility drops sharply. Beyond roughly 1,000 meters, natural light disappears entirely. Cameras must rely on artificial illumination, which only reaches limited distances. That constraint means mapping requires sonar rather than optical imaging. Sonar works well but produces different kinds of data, often needing careful interpretation before meaningful conclusions can be drawn. Pressure also increases steadily with depth. Roughly every 10 meters adds another atmosphere of pressure. At the depth of the Galathea Deep, that pressure becomes enormous. Equipment housings must be reinforced, seals must remain perfect, and any structural weakness quickly becomes a failure point. Even small design flaws can lead to implosion. Engineers spend years testing materials and designs specifically for deep-sea conditions. That careful preparation slows exploration, but it prevents catastrophic loss of instruments and data. Communication presents another limitation. Radio waves, which carry most wireless communication on land, do not travel efficiently through seawater. Acoustic signals are used instead, but they carry less bandwidth and often suffer interference from natural ocean noise. That means real-time high-definition video transmission is difficult at extreme depths. Data is frequently recorded locally and retrieved later. This delay reduces immediate feedback during missions and requires cautious planning. Then there is sheer scale. Oceans are vast, not just horizontally but vertically. Mapping every square kilometre at fine resolution would take enormous time, even with fleets of autonomous vehicles. Survey priorities are therefore established based on scientific importance, economic interest, or environmental monitoring needs. Deep trenches rank high scientifically, but low in terms of accessibility, so progress tends to be gradual. Space exploration is often compared with ocean exploration, sometimes with the claim that we know more about the moon than our own oceans. While that statement simplifies a complex reality, there is truth in it. Space missions, though technically challenging, operate in an environment where communication is straightforward once signals clear Earth's atmosphere. Instruments face vacuum and radiation, but not crushing pressure or corrosive salt water. Launch windows are predictable, whereas ocean missions must constantly adapt to weather, currents, and mechanical wear. Financial considerations also shape exploration patterns. Deep-sea missions require specialized ships, crews, maintenance infrastructure, and often international collaboration. Costs accumulate quickly. Funding agencies balance those expenses against potential benefits such as climate insights, resource assessments, or hazard monitoring. Trenches like the Galathea Deep offer high scientific value but relatively limited immediate economic return, which explains why expeditions are less frequent than curiosity alone might justify. Environmental protection concerns have grown as well. Earlier decades sometimes approached exploration with minimal ecological consideration. Current standards emphasize minimizing disturbance, especially in fragile deep ecosystems. Sampling methods are more selective, and non-invasive observation is preferred when possible. This ethical shift adds complexity to mission design, but protects environments that may recover slowly from disruption. Despite these challenges, technological progress continues steadily. Autonomous underwater vehicles can operate for extended periods without direct human control. Improved battery systems extend mission duration. Advanced sonar mapping produces increasingly detailed topographic models. Machine learning algorithms help interpret acoustic data more efficiently, identifying features that once required lengthy manual analysis. Even with these tools, unexpected findings remain common. Geological formations appear that do not fit established models. Biological samples reveal organisms adapted to pressure levels previously thought prohibitive for complex life. Chemical signatures suggest interactions between ocean water and underlying rock layers that influence nutrient cycles and carbon storage. Each discovery reinforces the idea that deep oceans remain active scientific frontiers rather than static environments. The phrase "last frontier" sometimes implies a dramatic boundary, but in ocean science it usually refers to persistent unknowns. Researchers are less interested in conquest language and more focused on understanding processes that influence global systems. Deep trenches contribute to earthquake generation, ocean circulation patterns, and long-term climate regulation. Studying them supports broader environmental knowledge rather than simple geographic curiosity. Public awareness of deep ocean research has grown slowly. Documentaries, remotely operated vehicle footage, and scientific outreach programs help translate technical findings into accessible narratives. Still, Compared with space missions, deep-sea exploration receives less sustained attention. Perhaps that is because oceans feel familiar at the surface. Beaches, ships, and coastal cities create an illusion of familiarity that does not extend to abyssal depths. Psychological factors also play a role. Darkness and depth can evoke discomfort. Some individuals experience mild unease even watching deep ocean footage. Scientists acknowledge this response but usually emphasize training and procedural familiarity. Exposure gradually replaces apprehension with professional focus. Still, the environment commands respect. That balance between curiosity and caution defines much of deep-sea research culture. Climate change has added urgency to ocean exploration. Deep waters store significant amounts of carbon dioxide and heat. Understanding how trenches participate in these processes helps refine climate models. Sediment layers preserve historical records of ocean conditions, offering clues about past climate shifts. Extracting and analysing those records requires precise sampling from challenging depths. Marine biodiversity research provides another incentive. Extremophile organisms living under high pressure, low temperature, and minimal light often possess biochemical adaptations with potential applications in medicine, biotechnology, and materials science. Enzymes stable under extreme conditions, for instance, attract industrial interest. Discoveries in trenches sometimes translate into practical innovations decades later. Geological hazards remain an additional focus. Subduction zones, where one tectonic plate slides beneath another, often coincide with deep trenches. Monitoring these regions helps assess earthquake and tsunami risk. The Philippine Trench, associated with the Galathea Deep, lies within an active tectonic area. Continuous observation improves understanding of stress accumulation and release along plate boundaries. From a logistical standpoint, exploration strategies continue evolving. Some missions prioritize broad mapping first, followed by targeted sampling. Others focus immediately on biological surveys. Collaborative international expeditions share costs and expertise, allowing more comprehensive coverage than single-nation projects might achieve. Data-sharing agreements increasingly ensure that findings benefit the global scientific community. Public interest sometimes peaks when unusual discoveries emerge, such as previously unknown species or striking geological formations. These moments provide opportunities for science communication, helping people appreciate both the excitement and the methodical patience involved. Most discoveries are incremental rather than dramatic, yet collectively they reshape understanding of ocean systems. Educational institutions are incorporating ocean literacy into curricula more actively. Awareness of ocean processes supports informed decision-making about environmental policy, fisheries management, and climate mitigation strategies. Trenches like the Galathea Deep serve as compelling case studies, demonstrating both the limits of current knowledge and the value of sustained research. Cultural perspectives vary globally. Coastal communities often maintain traditional knowledge about ocean behaviour, currents, and ecological patterns. Integrating that knowledge with scientific research can enrich understanding. While deep trenches lie far beyond traditional fishing zones, broader ocean awareness still influences how societies approach marine conservation. Technological crossover from other fields contributes as well. Advances in robotics, materials science, artificial intelligence, and energy storage all support deeper, longer missions. Improvements rarely occur in isolation. A battery innovation developed for electric vehicles, for example, may later enable longer autonomous underwater exploration. As attention gradually returns to the Galathea Deep specifically, it becomes clear why scientists regard it as part of a much larger story rather than an isolated curiosity. Its depth, geological setting, and biological potential intersect with global scientific questions. Understanding one trench helps refine models applicable to others, building a cumulative picture of deep ocean dynamics. And when that wider perspective settles in, the sense of the oceans as a remaining frontier begins to feel less like a dramatic label and more like a practical acknowledgement that exploration continues steadily, revealing complexity layer by layer, which naturally leads toward a closer look at where exactly the Galathea Deep sits within this vast underwater landscape, and why its location itself shapes so much of what scientists observe there. Understanding why the Galathea Deep continues to draw scientific attention becomes easier once its exact location is placed into context, as geography, tectonics, and ocean circulation all shape what happens there. The Galathea Deep lies within the Philippine Trench, an immense underwater depression in the western Pacific Ocean. This trench stretches roughly north to southeast of the Philippine archipelago, forming one of the most dramatic geological boundaries on the planet. Unlike surface features that can be seen easily on maps or satellite images, trenches like this exist entirely below the ocean's surface, hidden from casual observation, which partly explains why they remained unknown until relatively recent scientific exploration. The deepest measured point of this trench, known as the Galathea Deep, reaches a depth of more than 10,000 metres below sea level. Numbers alone can feel abstract. So many scientists use comparisons to make the scale clearer. If Mount Everest were placed there, its summit would still remain submerged. Commercial aircraft typically cruise at altitudes around 10 to 12 kilometres, meaning the depth of the Galathea Deep approaches that same vertical scale, only inverted beneath the ocean. These comparisons are not dramatic exaggerations. They help translate a difficult dimension into something more relatable. Geographically, the trench sits to the east of the Philippines, bordering a region where tectonic plates interact constantly. The Philippine sea plate is subducting beneath the Philippine mobile belt, creating the trench itself. Subduction zones like this are among the most geologically active areas on Earth. Earthquakes, volcanic activity, and slow crustal deformation occur over long timescales. This activity influences not only geology, but also water chemistry, sediment movement, and biological habitats at extreme depths. Ocean currents also play a role in shaping the environment. Surface currents above the trench interact with deeper circulation patterns that transport nutrients, sediments, and dissolved gases. Some of this material eventually settles into the trench, creating layers that preserve environmental history. Sediment cores extracted from trenches can reveal climate fluctuations, volcanic eruptions, and biological productivity changes spanning thousands or even millions of years. That historical archive attracts researchers from multiple disciplines. Mapping the exact contours of the trench has taken decades. Early expeditions relied on weighted lines and primitive echo-sounding equipment. Accuracy was limited, and measurements varied widely. Later sonar mapping refined the profile, revealing steep walls, uneven slopes, and isolated basins within the trench system. Even today, complete high-resolution mapping remains incomplete. Autonomous underwater vehicles and improved multi-beam sonar continue filling gaps slowly. The trench's remote location complicates logistics. Research vessels must travel considerable distances from major ports, carrying specialized equipment, fuel reserves, and scientific personnel. Weather patterns in the Western Pacific can change rapidly, particularly during typhoon seasons. Scheduling expeditions requires careful planning around seasonal conditions, ship availability, and funding cycles. These constraints reduce the frequency of direct observation. International collaboration has become common for expeditions in this region. The trench lies near several national jurisdictions, and scientific interest spans many countries. Shared missions distribute costs and expertise while promoting data transparency. Oceanography has long benefited from cooperative research because marine systems do not align neatly with political boundaries. Cartographically, the Galathea Deep appears as a narrow indentation on ocean floor maps. Without depth shading or three-dimensional modelling, it might look modest. Only when vertical exaggeration is applied does the scale become apparent. Visualization techniques matter greatly in communicating trench features to broader audiences. Scientists increasingly use digital terrain models and interactive graphics to convey depth relationships more intuitively. The surrounding marine environment varies significantly with depth. Surface waters support typical tropical marine ecosystems influenced by sunlight, temperature gradients, and nutrient availability. Descending into the trench, conditions shift progressively toward darkness, cold, and increasing pressure. Each depth zone hosts organisms adapted specifically to those conditions. The deepest sections remain the least understood biologically. Satellite observation helps indirectly. While satellites cannot see the trench floor, they measure subtle variations in sea surface height caused by gravitational differences from underwater features. These measurements guide mapping priorities by indicating where significant topographic structures exist below. Combining satellite altimetry with sonar surveys produces more complete models than either method alone. Another aspect of location involves seismic monitoring. Because the trench marks an active plate boundary, seismographs placed on nearby islands and ocean bottom instruments track tectonic activity continuously. These data contribute to earthquake research and tsunami warning systems. Understanding stress accumulation along the trench improves hazard assessment for coastal populations. Chemical oceanography studies also benefit from knowing the trench's exact position relative to currents and geological formations. Water samples taken at various depths reveal dissolved mineral concentrations, organic matter levels, and microbial activity patterns. Some chemical signatures indicate interactions between seawater and crustal rocks, processes that can influence long-term carbon cycling. Biological surveys depend heavily on location-specific information as well. Species distribution often correlates with trench depth gradients, sediment composition, and proximity to hydrothermal or cold seep activity. While the Galathea Deep is not primarily known for hydrothermal vents, localized chemical anomalies occasionally appear, prompting further investigation. The trench's position in the Western Pacific places it within one of the world's most complex marine regions. Island arcs, basins, ridges and trenches interconnect through tectonic processes. Understanding any single feature requires situating it within this broader geological framework. That interconnectedness explains why multidisciplinary teams often participate in expeditions. Navigation technology has improved accuracy dramatically compared with early exploration. Global positioning system integration allows precise surface positioning, while underwater acoustic navigation systems track submersibles relative to the ship. These advancements reduce uncertainty in sampling locations, enabling repeat observations over time. Longitudinal studies depend on that consistency. Environmental monitoring initiatives now include deep ocean components more regularly. Climate models incorporate abyssal temperature trends, salinity variations, and carbon storage estimates. Trenches like the Galathea Deep contribute data points essential for refining those models. Small measurement errors at depth can propagate into larger uncertainties if not corrected carefully. Public awareness of this specific trench remains relatively limited compared with the Mariana Trench. Media coverage often focuses on record-breaking depth figures, and while the Galathea Deep is exceptionally deep, it does not hold the absolute global record. Still, scientists recognise its importance because each trench provides distinct geological and biological information. The name itself carries historical significance. It commemorates the Danish research vessel Galathea, whose mid-20th century expeditions advanced deep-sea exploration considerably. Naming conventions in oceanography often reflect expedition vessels, researchers, or geographic features. These names help track discovery history and maintain continuity in scientific literature. Technological advances continue reshaping exploration strategies. Remotely operated vehicles provide real-time video, sampling capability, and environmental sensors. Autonomous vehicles extend range and duration beyond what tethered systems allow. Hybrid approaches combine both, optimizing data collection while managing risk. Educational outreach sometimes includes virtual dives reconstructed from sonar data and video footage. These experiences help students and the public visualize environments otherwise inaccessible. Increased familiarity may encourage future careers in ocean science, addressing workforce needs in marine research. Economic interests occasionally intersect with deep-sea research. Mineral resource assessments, for instance, consider seabed deposits. Environmental impact considerations remain central, and most trench regions are treated cautiously due to ecological sensitivity. Scientific understanding informs policy discussions about sustainable resource management. Looking again at the map, the Galathea Deep sits quietly, unseen beneath kilometres of water, yet influencing scientific conversations far beyond its immediate location. Its position at a tectonic boundary within complex ocean circulation systems and among largely unexplored abyssal habitats ensures ongoing interest. Researchers return not because the site is fully understood, but precisely because it is not. And once that geographical context settles in place, the next natural curiosity often shifts towards scale itself, because knowing where something is inevitably raises the question of just how deep it really goes, and what those depths actually mean when translated into everyday human experience. Once the location of the Galathea Deep is clear on a map, the next question usually comes naturally, and it sounds simple on the surface. Just how deep is it really? Numbers get mentioned quickly in scientific discussions, often somewhere slightly above 10,000 metres below sea level. That figure is accurate enough for general conversation, yet it rarely conveys the physical reality of what that depth means. Human intuition evolved in environments where vertical distance rarely exceeds a few hundred metres. Even skyscrapers, tall as they feel, only reach a fraction of a kilometre. Translating a 10-kilometre descent into something mentally tangible takes a bit more explanation. Imagine standing at sea level and descending steadily downward. The first few hundred metres would still fall within the zone where sunlight penetrates. Divers occasionally reach parts of this region, though already under strict limits. By around 1,000 metres, natural light fades almost entirely. Beyond that point you enter permanent darkness. There is no sunrise or sunset there, no visual reference for day or night. Artificial lights create small illuminated circles surrounded by black water. This visual isolation alone often surprises people when they first consider deep ocean conditions. Pressure increases quickly during that descent. Every 10 metres adds roughly 1 atmosphere of pressure, similar to what you feel at Earth's surface. At a depth of 10,000 metres, pressure exceeds 1,000 atmospheres. That means each square centimetre of an object experiences a force equivalent to hundreds of kilograms pressing inward. Materials that feel solid and reliable at the surface behave very differently under such conditions. Metals flex, seals compress, and microscopic structural imperfections can become failure points. Engineers designing submersibles for these depths account for that pressure constantly. Comparisons with familiar landmarks help translate scale. Mount Everest, the tallest mountain above sea level, stands just under 9 kilometres high. If placed inside the Galathea Deep, its peak would still sit more than a kilometre below the ocean surface. Commercial airplanes typically cruise at around 10 to 12 kilometres altitude. If one could somehow descend vertically from cruising altitude straight down into the trench, the total vertical travel would roughly mirror that journey in reverse. These comparisons are not meant to dramatise, but to provide a reference frame. Another useful comparison involves everyday travel speed. Driving a car downward at highway speed, which is already an unrealistic scenario, would still take many minutes to reach such depths. In reality, deep submersibles descend far more slowly, sometimes taking several hours. The pace reflects caution. Rapid descent increases risk, both mechanically and operationally. Controlled movement ensures systems remain stable and allows time for adjustments. Temperature shifts accompany the descent as well. Surface waters in tropical regions near the Philippines may feel warm and comfortable. Descending deeper, temperatures drop steadily until stabilising just above freezing in abyssal zones. This cold remains consistent year-round because sunlight never reaches those depths. The stability might sound reassuring, yet it contributes to the unique ecological conditions scientists study. Sound behaves differently underwater compared with air. Deep environments carry acoustic signals efficiently over long distances. That property supports sonar mapping and communication, but also introduces ambient noise from geological activity, marine life, and distant human operations. Researchers analysing acoustic data sometimes detect unexpected patterns that require careful interpretation. Depth also influences water density and chemistry. Dissolved gases behave differently under pressure. Nutrient distribution shifts with currents and sedimentation. Microbial communities adapt to chemical conditions that would seem hostile elsewhere. These factors make trenches valuable natural laboratories for studying extremophile life and geochemical processes. Visibility remains limited regardless of technology. Even powerful lights illuminate only small volumes of water. Particles suspended in deep currents scatter light, reducing clarity further. Video footage from deep expeditions often appears calm and slow-moving, yet scientists viewing it recognize the intense conditions surrounding that tranquil image. The concept of time changes subtly during deep missions. Descents take hours, sampling procedures proceed carefully, and ascent schedules must account for equipment safety. Crewed missions add physiological considerations. Although submersible cabins maintain surface pressure internally, crew members still experience psychological effects from isolation and prolonged darkness. Mapping techniques reflect these constraints. Multi-beam sonar systems send sound pulses downward, measuring return times to calculate depth. Data processing then converts those measurements into three-dimensional terrain models. Resolution improves with each technological generation, yet mapping an entire trench at high detail remains a long-term project. Another point worth noting is variability. The figure often quoted for the Galathea Deep represents the deepest confirmed measurement, but surrounding areas vary considerably. Slopes, ridges, and sediment layers create a complex landscape rather than a uniform pit. geological activity continuously reshapes these features over long timescales. Sediments accumulating in trenches come from multiple sources. Surface productivity produces organic matter that sinks slowly. Rivers deliver minerals and organic particles to coastal waters, which eventually reach deeper regions. Volcanic ash occasionally settles from atmospheric eruptions. Each layer records environmental history, providing valuable information for climate and geological studies. Biological life at these depths challenges expectations. Organisms adapt structurally and chemically to withstand pressure, darkness, and limited food supply. Some species rely on chemosynthesis rather than photosynthesis, deriving energy from chemical reactions instead of sunlight. Discoveries in such environments expand understanding of life's adaptability, with implications extending even to astrobiology. Equipment design must anticipate corrosion from salt water, pressure-induced deformation, and temperature stability. Redundant systems reduce risk. Recovery protocols assume that not every mission will proceed perfectly. Deep-sea research carries inherent uncertainty, but careful engineering minimizes catastrophic outcomes. Public imagination sometimes associates deep trenches with dramatic unknown creatures or sudden hazards. In practice, scientific work emphasizes measurement, observation, and cautious interpretation. Surprises occur, yet they're usually incremental rather than cinematic. The persistent unknowns rather than sudden events sustain scientific interest. Historical measurement accuracy has improved steadily. Early expeditions produced approximate depths with significant uncertainty margins. Modern sonar, satellite altimetry integration, and direct submersible readings have refined those estimates. Ongoing work continues adjusting details as instrumentation advances. Environmental monitoring programs now incorporate abyssal measurements more consistently. Temperature, salinity, and chemical composition at depth contribute to global ocean circulation models. These models influence climate predictions and resource management decisions. Deep trenches, though remote, play roles in broader planetary systems. Educational outreach sometimes highlights depth comparisons to foster ocean literacy. Understanding scale encourages appreciation for marine conservation and scientific research funding. Visual aids, interactive simulations, and virtual dives help translate abstract measurements into relatable experiences. Psychological responses to depth vary widely. Some individuals find the idea unsettling, possibly due to darkness and perceived isolation. Scientists typically develop professional detachment, focusing on data rather than emotional interpretation. Training emphasizes familiarity with procedures, which reduces anxiety during missions. Technological innovation continues expanding exploration capacity. Improved battery density extends autonomous vehicle endurance. Stronger composite materials enhance pressure resistance. Data processing advances accelerate interpretation. These developments gradually reduce barriers that once limited deep ocean study. Looking again at the number itself, 10,000 meters remains an extraordinary vertical distance by human standards. Yet within scientific discussion, it becomes simply a parameter, one variable among many influencing environmental conditions. That shift from awe to analysis reflects how familiarity develops through sustained research. And once depth begins to feel less abstract and more measurable, attention naturally turns toward how that measurement was first established, because every scientific number carries a history behind it, including the expeditions, instruments, and individuals who first identified the Galathea Deep and gave it the name still used today. Once the depth itself begins to feel more concrete rather than abstract, it becomes natural to look back at how scientists first realised that a place like the Galathea Deep even existed, because discoveries of this kind rarely happen in a single dramatic moment. Instead, they unfold gradually through careful measurement, technical innovation, and sometimes a fair amount of patience. The Galathea Deep owes its name to a Danish research vessel, HDMS Galathea, which undertook one of the most ambitious oceanographic expeditions of the mid-20th century. That expedition did not set out simply to break records or chase headlines. Its primary aim was scientific observation, systematic measurement, and a broader attempt to understand deep ocean environments that, at the time, were still largely theoretical in many respects. The second Galathea expedition, conducted between 1950 and 1952, came at an interesting historical moment. World War II had recently ended, naval technologies had advanced significantly, and scientific communities were beginning to apply wartime engineering innovations toward peaceful research. Echo-sounding equipment, pressure-resistant materials, and navigation tools developed during the war suddenly had new applications in oceanography. Denmark, despite being a relatively small maritime nation, maintained a strong tradition of marine science, and the Galathea expedition reflected that heritage. The vessel itself was not enormous by modern research standards, but it was carefully outfitted. Laboratories, sampling gear, sonar equipment, and living quarters for scientists were integrated into the ship's design. Expeditions of that era required months or even years at sea, so self-sufficiency was essential. Supplies, spare parts, and research materials had to be stocked in advance. Communication with land was limited compared with modern satellite systems, so crews operated with considerable autonomy. One important point often overlooked is that early deep-sea expeditions did not assume they would necessarily find extreme depths. Ocean floor mapping in the early 20th century was incomplete. Some trenches were known, but their precise depth profiles remained uncertain. Each measurement carried the possibility of revising existing maps significantly. Scientists approached their work methodically, aware that reliable data mattered more than dramatic announcements. Echo sounding, the primary measurement technique used during the Galathea expedition, involves sending sound pulses downward and timing their return after bouncing off the seafloor. While the principle seems straightforward today, equipment reliability, calibration accuracy, and environmental noise all complicated measurements. Water temperature, salinity, and pressure affect sound speed, requiring careful correction factors. Early researchers devoted substantial effort to verifying these adjustments. When the Galathea expedition recorded unusually large depth readings east of the Philippines, initial reactions were cautious. Extraordinary measurements required confirmation. Repeated soundings, equipment checks, and cross-verification with different instruments helped establish confidence. Only after consistent readings did scientists begin recognizing that they were documenting one of the deepest points in that trench system. Naming conventions in oceanography often honor the vessels or expeditions responsible for discovery. In this case, Galathea Deep acknowledged the ship whose crew conducted the measurements. Such naming practices help maintain historical continuity. Scientific literature frequently references these original expeditions when discussing subsequent findings, linking modern research with earlier groundwork. Life aboard the research vessel followed a disciplined routine. Scientists worked in shifts, monitoring instruments, processing samples, and recording observations. Oceanographic expeditions combine technical precision with endurance. Long periods at sea test both equipment and personnel. Weather conditions, mechanical maintenance, and daily operational logistics all influence productivity. Crews develop structured schedules to maintain efficiency. Sampling techniques extended beyond depth measurement. Sediment cores, water samples, and biological specimens were collected whenever possible. Early deep-sea biology was still developing as a field. There had been debates earlier in the century about whether complex life could exist at extreme depths. Expeditions like Galathea provided empirical evidence demonstrating that life persists even under immense pressure. Technological limitations of the time meant that direct visual observation of the deepest areas was rare. Crude submersibles capable of reaching such depths were still experimental. Most information came from acoustic data and physical samples retrieved indirectly. Despite those limitations, the expedition contributed significantly to understanding ocean floor topography. Navigation accuracy also deserves mention. Modern GPS systems allow precise positioning within meters. Mid-20th century expeditions relied on celestial navigation, radio beacons, and dead reckoning. Position estimates carried greater uncertainty. Researchers documented these uncertainties carefully, which later allowed updated mapping with improved positioning systems. The broader scientific impact of the Galathea expedition extended beyond the Philippine Trench. The vessel circumnavigated the globe, collecting data from multiple ocean basins. Findings contributed to developing theories about plate tectonics, sediment distribution, and deep-sea ecology. At the time, plate tectonic theory itself was still gaining acceptance. Oceanographic data played a crucial role in confirming continental drift mechanisms. Funding such expeditions required governmental support and international scientific collaboration. Post-war enthusiasm for scientific advancement helped secure resources. Public interest in exploration, both terrestrial and marine, created a favourable environment for large-scale research initiatives. Educational outreach following the expedition shared findings widely, strengthening public awareness of ocean science. Media coverage of the expedition tended to emphasise discovery and adventure, yet scientists themselves maintained a measured tone. They recognised that each new measurement added to a cumulative body of knowledge rather than providing final answers. This cautious communication style remains characteristic of oceanographic research today. Another lasting contribution involved equipment development. Challenges encountered during the expedition informed later engineering improvements. Pressure housings, sampling devices, and sonar calibration techniques evolved partly through lessons learned on voyages like Galathea's. Scientific progress often advances through iterative refinement rather than sudden breakthroughs. The expedition also demonstrated the importance of interdisciplinary teams. Geologists, biologists, chemists, physicists, and engineers collaborated closely. Understanding deep oceans requires integrating multiple perspectives. That collaborative model continues in modern expeditions, often expanded internationally. Historical records from the voyage include detailed logs, instrument calibration notes, and personal journals. These documents provide valuable context for contemporary researchers revisiting earlier data. Changes observed over decades sometimes rely on comparing modern measurements with those original records. Environmental awareness has shifted since the 1950s. Early expeditions prioritized discovery, sometimes with limited ecological consideration. Today's researchers emphasize minimal disturbance and long-term environmental monitoring. Still, the foundational data collected during the Galathea expedition remains scientifically valuable. Educational institutions frequently reference the expedition when discussing the history of oceanography. It illustrates how persistence, technical ingenuity, and international cooperation contribute to scientific understanding. Students studying marine science often encounter these historical narratives early in their training. Technological contrast between then and now highlights how rapidly ocean science evolves. Modern remotely operated vehicles transmit high-definition video from depths unimaginable during the 1950s. Autonomous sensors record continuous environmental data, yet the fundamental curiosity driving exploration remains consistent. Looking back, the naming of the Galathea Deep reflects both achievement and humility. The expedition identified something significant, but did not claim complete understanding. That measured approach set a precedent for subsequent research in the region. The scientific attention gradually expanded beyond initial discovery toward ongoing investigation. Researchers began asking not just how deep the trench was, but why it continued attracting repeated expeditions, because initial measurements answered location and depth questions, while opening a much broader set of inquiries about geology, biology, chemistry, and environmental processes that keep scientists returning even decades later. Once the first measurements confirmed just how deep the Galathea Deep actually was, the natural assumption might have been that the discovery phase was finished. The trench had been mapped, the depth had been recorded, and the scientific community could move on. Yet that is not how ocean research tends to work. Discovering a place is rarely the end of the process. In many cases it marks the beginning of sustained observation, repeated measurements, and long-term study. The Galathea Deep fits that pattern very clearly, because each visit tends to raise new questions rather than closing existing ones. One major reason scientists return repeatedly involves geological activity. The Philippine Trench forms along a tectonic boundary, where one plate descends beneath another. These subduction zones are dynamic over long timescales. Earthquakes occur, sediment layers shift, and the physical shape of the trench changes gradually. A single survey offers only a snapshot. Continued monitoring helps scientists understand rates of movement, stress accumulation, and potential links to seismic hazards affecting nearby regions. Coastal populations in the Western Pacific depend on accurate hazard assessments, so maintaining updated data carries practical importance beyond academic curiosity. Sediment accumulation provides another strong motivation. Material constantly settles into deep trenches from multiple sources. Organic particles sink from surface ecosystems. Volcanic ash occasionally arrives after eruptions. Rivers transport minerals that eventually disperse across ocean basins. Each layer records environmental conditions at the time of deposition. Extracting sediment cores from the Galathea Deep allows researchers to reconstruct past climate conditions, ocean productivity, and geological events. Because deposition continues slowly but steadily, repeated sampling over decades reveals changes that a single expedition could never capture. Biological interest also remains high. Early deep-sea exploration established that life exists under extreme pressure, but understanding how that life functions continues evolving. Microorganisms adapted to high pressure often possess biochemical traits unlike those of surface organisms. Enzymes stable under intense pressure and low temperature attract attention from biotechnology researchers. Pharmaceutical studies sometimes explore compounds produced by extremophile microbes. Each expedition has the potential to identify new species or metabolic pathways, which explains why biological sampling remains a consistent priority. Technological progress itself encourages revisiting previously studied sites. Instruments improve continuously. Cameras capture clearer images in low-light environments. Sensors detect chemical traces once below measurement thresholds. Autonomous vehicles extend operational range and endurance. Data collected decades ago may lack resolution compared with modern standards. Revisiting the Galathea Deep with updated equipment often reveals details that earlier expeditions simply could not observe. Long-term environmental monitoring has become increasingly important in recent decades. Climate change research recognizes that deep oceans store significant amounts of heat and carbon dioxide. Trenches may act as sinks for certain materials, influencing global cycles. Repeated measurements of temperature, salinity, dissolved gases, and nutrient levels contribute to refining climate models. Small variations at depth can influence large-scale ocean circulation patterns over time. Another factor involves anomaly investigation. Occasionally, data collected during one expedition show unexpected results. Chemical concentrations may differ from predictions. Acoustic readings may suggest geological movement. Biological samples may include unfamiliar organisms. Rather than assuming measurement error immediately, scientists often schedule follow-up missions to confirm or clarify those anomalies. Verification strengthens scientific conclusions. Equipment testing represents a practical reason as well. Extreme environments provide valuable proving grounds for new technologies. Pressure-resistant materials, advanced sensors, and navigation systems all benefit from real-world testing under challenging conditions. Research institutions sometimes coordinate technology trials with scientific missions, maximizing efficiency while advancing engineering capabilities. Interdisciplinary collaboration has expanded substantially since the original Galathea expedition. Modern missions often include geologists, biologists, chemists, physicists, engineers, and climate scientists working together. Each discipline approaches the trench with distinct questions. Combining perspectives increases the likelihood of meaningful discoveries. The trench serves as a shared laboratory where multiple research agendas intersect. Educational training also plays a role. Graduate students and early career researchers gain valuable experience participating in deep-sea expeditions. Exposure to fieldwork complements laboratory study. Handling real equipment, interpreting live data, and adapting to operational constraints prepare scientists for future research leadership. Expeditions therefore support both discovery and professional development. Data continuity matters greatly in environmental science. Single measurements provide limited insight into trends. Long-term data sets allow detection of gradual changes that short-term studies might miss. Returning to the same trench periodically ensures consistency in observation sites, improving statistical reliability of analyses. Public communication sometimes benefits from renewed exploration as well. Documented expeditions capture public imagination and help explain ocean science relevance. Educational outreach associated with missions can inspire interest in marine conservation, climate awareness, and scientific careers. While outreach is not the primary motivation, it often accompanies major expeditions. There is also a psychological dimension within the scientific community. Unresolved questions tend to attract continued attention. The Galathea Deep consistently presents puzzles rather than final answers. That ongoing uncertainty maintains professional interest. Scientists generally prefer incomplete understanding over assumed certainty because unresolved questions drive progress. Policy considerations occasionally intersect with research planning. Marine resource management, conservation strategies, and hazard mitigation policies rely on accurate environmental data. Governments and international organizations support research that informs these decisions. Deep trenches contribute indirectly through climate modeling, biodiversity assessment and geological monitoring. Advances in computing have transformed data analysis capabilities. Historical data sets can now be reprocessed using modern algorithms. Comparing old and new data sometimes highlights trends previously unnoticed. This retrospective analysis often prompts additional fieldwork to confirm interpretations. Another subtle motivation involves verification of scientific models. Theoretical predictions about pressure effects, chemical equilibria, and biological adaptation require empirical confirmation. Extreme environments test the limits of those models. The Galathea Deep provides conditions difficult to replicate experimentally, making field observation essential. Operational experience accumulates gradually. Each expedition improves logistical planning, equipment deployment strategies, and safety protocols. Institutional knowledge develops over time. Returning to familiar sites allows refinement of procedures, increasing efficiency and reducing risk. International cooperation has strengthened in marine science. Shared expeditions distribute financial burden while enhancing data accessibility. Collaborative frameworks encourage standardization of measurement techniques, improving comparability across studies. The Galathea Deep often features in multinational research agendas for precisely these reasons. Scientific curiosity itself should not be underestimated. Researchers dedicate careers to understanding natural systems. Persistent unknowns represent opportunities rather than frustrations. Returning to the trench reflects professional commitment to gradual discovery rather than expectation of immediate breakthroughs. Environmental ethics increasingly influence research design. Minimizing disturbance while maximizing knowledge requires careful planning. Repeat visits help evaluate whether previous activities affected local ecosystems. Responsible stewardship has become an explicit objective alongside scientific inquiry. Technological redundancy also improves data reliability. Multiple instruments measuring similar parameters reduce uncertainty. Follow-up missions confirm whether earlier findings were consistent or anomalous. Scientific credibility depends heavily on reproducibility. Funding cycles contribute practical timing constraints. Grants often support multi-year research programs with scheduled field components. The Galathea Deep frequently appears within broader Pacific research initiatives, ensuring periodic attention. As these various motivations combine, a pattern becomes clear. Scientists return not out of habit, but because the trench continues offering valuable data across multiple disciplines. Each expedition adds incremental understanding while revealing additional complexity. And as attention settles on the reasons for repeated visits, discussion naturally shifts toward one of the most immediate physical challenges researchers face there, because the environment itself imposes extreme conditions, particularly the immense pressure that shapes every aspect of exploration and biological survival at those depths. When discussion turns from why scientists keep returning to what they actually encounter down there, pressure almost always becomes the first topic because it shapes everything else. Temperature, chemistry, biology, engineering limits, even how long equipment can safely remain in operation, all connect back to pressure. It is not a dramatic exaggeration to say that pressure defines life and research conditions in places like the Galathea Deep. And yet, despite how often the numbers are quoted, the reality of that pressure remains difficult to picture clearly. At sea level, the human body experiences one atmosphere of pressure. It feels normal because we evolved with it. The air presses evenly on all sides, so it rarely draws attention. Water behaves differently. It is far denser than air, so pressure increases quickly as depth increases. Roughly every 10 metres of descent adds another atmosphere. By the time you reach 100 metres, pressure has multiplied tenfold. At 1,000 metres, it has increased roughly 100 times. Continue that progression down to around 10,000 metres, and the pressure exceeds 1,000 atmospheres. That means every square centimetre of a surface experiences force equivalent to hundreds of kilograms, pushing inward constantly. The effect is steady rather than sudden, which sometimes makes it seem less dramatic in explanation than it actually is. Engineers designing equipment for those depths treat pressure as the primary constraint. Materials must resist compression without deforming. Seals must remain perfect despite continuous stress. Even microscopic flaws in construction can propagate quickly under such conditions. Human divers cannot approach those depths directly. Even advanced technical diving remains limited to a few hundred metres under carefully controlled conditions. Beyond that, submersibles or remotely operated vehicles become essential. Crewed submersibles maintain internal pressure close to surface levels, protecting occupants from direct compression. Their hulls, however, must withstand the full external force. Spherical shapes are common because they distribute pressure evenly, reducing stress concentrations. Material selection becomes critical. Steel, titanium, specialized composites, and ceramics each offer advantages and limitations. Titanium, for example, combines strength with corrosion resistance, but remains expensive and difficult to manufacture in large pressure-resistant structures. Composite materials provide lighter weight, but require extensive testing to ensure long-term reliability under repeated stress cycles. Pressure influences not just mechanical structures, but also electronics. Conventional housings may fail if seals degrade. Oil-filled pressure compensation systems sometimes allow components to operate without rigid casings, equalizing internal and external pressure. This approach reduces structural stress but requires careful design to prevent contamination or electrical issues. Biological adaptation at such depths continues to fascinate researchers. Organisms living there have evolved biochemical mechanisms allowing cellular processes to function under immense compression. Proteins maintain stability, membranes retain flexibility, and metabolic pathways operate despite conditions that would disrupt surface organisms. These adaptations are not merely curiosities. They inform biotechnology research, particularly enzyme design for industrial processes operating under high pressure. Fish species discovered in deep trenches often lack gas-filled swim bladders, common in shallower species. Gas compresses under pressure, so alternative buoyancy strategies evolve. Gelatinous tissues, specialized lipids, and structural modifications allow neutral buoyancy without relying on compressible gases. These anatomical features also influence locomotion and feeding behavior. Microbial life presents another area of interest. Pressure-loving microorganisms called piezophiles thrive where surface bacteria would fail. Their enzymes function efficiently at pressures that would denature typical proteins. Studying these organisms helps expand understanding of life's adaptability, with implications extending beyond Earth, particularly in astrobiology discussions about subsurface oceans on icy moons. Chemical reactions behave differently under extreme pressure. Solubility of gases increases, reaction rates shift, and equilibrium conditions change. These effects influence nutrient cycling, carbon storage, and mineral formation in deep ocean environments. Geochemists analyze water and sediment samples carefully to interpret these pressure-driven processes. Operational planning for expeditions incorporates pressure considerations constantly. Descent rates are controlled to prevent structural shock. Equipment testing often involves pressure chambers simulating deep conditions before deployment. Even then, unexpected failures occasionally occur, reinforcing the need for redundancy and conservative design margins. Recovery of damaged equipment presents challenges. Imploded housings scatter fragments, complicating retrieval. Investigating failure causes becomes a detailed forensic exercise involving material analysis, stress modelling, and design review. Lessons learned contribute to improved future equipment. Pressure also affects acoustics. Sound travels efficiently in deep water, but pressure gradients influence propagation speed and direction. Sonar systems must account for these variations to maintain mapping accuracy. Calibration procedures include environmental measurements precisely for this reason. Temperature and pressure interact closely. Deep waters remain cold, but pressure slightly alters freezing points and fluid behaviour. These subtle effects matter in chemical analysis and biological studies. Researchers track temperature profiles carefully alongside pressure data. Human perception sometimes struggles with the concept because pressure at depth cannot be experienced directly without specialised equipment. Simulations in hyperbaric chambers approximate conditions but remain limited compared with natural trench environments. Scientists therefore rely heavily on instrumentation rather than direct sensation. Psychological responses still arise, particularly among crew members monitoring missions from the surface. Knowing that equipment operates under such extreme conditions introduces a constant awareness of potential failure. Training and experience mitigate anxiety, yet respect for environmental forces remains evident in operational culture. Engineering safety factors tend to be conservative. Structures are often rated for pressures exceeding expected operational limits. This redundancy increases reliability but also cost. Budget considerations sometimes influence mission scope, balancing scientific ambition with practical constraints. Comparisons occasionally help illustrate magnitude. Standing beneath a stack of large trucks balanced on a small platform approximates the compressive force experienced at extreme depths, though even that analogy remains imperfect. The key takeaway is consistency of force rather than sudden impact. Continuous compression defines the environment. Pressure gradients also influence sediment compaction. Layers deposited over long periods compress gradually, altering density and chemical composition. Sediment cores extracted from trenches reveal these changes clearly, providing historical environmental records. Equipment lubrication behaves differently under high pressure. Fluids compress slightly, viscosity changes, and seals require careful compatibility testing. Mechanical components must operate reliably despite these altered properties. Electrical insulation requires special consideration. Pressure can force water into microscopic gaps, risking short circuits. Protective coatings, pressure-tolerant connectors, and redundant insulation layers address these risks. Bioluminescent organisms occasionally appear in deep trench footage. Pressure influences light-producing chemical reactions, yet many species maintain consistent luminescence. Researchers study these systems for insights into biochemical stability. Communication systems rely heavily on acoustic transmission. Pressure gradients affect signal propagation, requiring adaptive modulation techniques. Engineers continuously refine these systems to improve reliability. Long-term monitoring equipment sometimes remains deployed for months or years. Pressure stability helps maintain consistent environmental conditions, but mechanical wear still occurs. Scheduled maintenance and periodic retrieval ensure data continuity. As the reality of pressure becomes clearer, the environment begins to feel less abstract and more physically grounded. Every scientific instrument, biological organism and geological structure in the Galathea Deep exists under that constant compressive force. Understanding it explains much of what researchers observe, and once pressure settles into the picture as the defining physical constraint, attention naturally shifts toward another equally persistent characteristic of that environment, because beyond the force pressing inward, there is also the complete absence of sunlight, a darkness that shapes perception, biology, and exploration just as profoundly. When pressure becomes familiar enough as a concept, another environmental factor begins to stand out just as strongly, and that is the complete absence of natural light. Down at the depth of the Galathea Deep, sunlight simply never arrives. It does not fade gradually into dim twilight the way evening does at the surface. It disappears entirely long before reaching those depths. This constant darkness is not temporary or seasonal. It has persisted continuously for millions of years, shaping biological evolution, exploration methods, and even the psychological frameworks scientists bring with them when they study such environments. Sunlight penetrates ocean water only to a limited extent. In clear tropical waters, some light reaches perhaps 200 meters. Beyond that, illumination drops sharply. By around 1,000 meters, natural light is essentially gone. The Galathea Deep lies far deeper than that threshold. The result is an environment where day and night no longer exist in any meaningful sense. Organisms living there do not rely on sunlight cycles. Geological processes continue unaffected by solar rhythms. Even temperature remains stable, because solar heating never reaches those depths. For scientists, darkness introduces immediate practical challenges. Cameras require powerful artificial lights, yet those lights illuminate only a small area. Suspended particles in deep water scatter light, reducing clarity. Video footage often appears calm and slow-moving, but researchers viewing it know that what they see represents just a tiny illuminated pocket surrounded by vast unseen space. That limited visibility shapes how exploration proceeds. Movements remain cautious, navigation relies heavily on sonar, and spatial awareness depends on instruments rather than vision. Artificial lighting systems must balance brightness with energy consumption. Submersibles and remotely operated vehicles carry finite power supplies. High-intensity lights drain batteries quickly and generate heat that must be managed carefully. Engineers design lighting arrays to maximize efficiency while maintaining image quality. Even then, exploration often prioritizes essential observations rather than continuous illumination. Sonar mapping compensates for visual limitations. Acoustic signals travel efficiently through water, allowing researchers to construct detailed terrain models. However, sonar produces indirect data requiring interpretation. Scientists convert echo timings into depth profiles, contour maps, and three-dimensional reconstructions. Visual confirmation sometimes follows, but initial understanding frequently comes from acoustic analysis rather than direct observation. Biological adaptation to darkness presents one of the most interesting scientific areas. Many deep-sea organisms either lack functional eyes or possess highly specialized visual systems adapted to minimal light. Some species rely on other senses entirely, detecting vibrations, chemical gradients, or pressure changes to navigate and locate food. Evolution in perpetual darkness leads to anatomical features that differ significantly from surface organisms. Bioluminescence becomes particularly important in such environments. Many deep-sea creatures produce their own light through chemical reactions. This light serves multiple purposes. Some species use it to attract prey, others to communicate, and some as a defensive mechanism to confuse predators. The chemistry behind bioluminescence remains an active research topic, partly because of potential applications in medical imaging and biochemical analysis. Human perception of darkness often carries emotional associations. On land, darkness suggests night, rest, or occasionally uncertainty. In deep ocean trenches, darkness has no daily cycle. It simply exists continuously. Scientists working with deep-sea footage sometimes report an initial sense of disorientation when reviewing extended recordings. Over time, professional familiarity replaces that reaction, but the environment retains a distinct character. Navigation without visual reference requires precise instrumentation. Inertial navigation systems, Doppler velocity logs, acoustic positioning beacons and pressure sensors all contribute to maintaining orientation. Redundancy remains essential. If one system fails, others must compensate. Loss of navigation capability at extreme depths can complicate recovery operations significantly. Darkness also affects thermal stability. Without sunlight, temperature fluctuations remain minimal. Deep ocean temperatures typically hover just above freezing, creating a relatively stable thermal environment. This stability influences biological metabolism, chemical reaction rates, and material performance. Engineers account for consistent low temperatures when designing equipment. Sediment deposition patterns sometimes become easier to study precisely because sunlight-driven biological activity remains absent. Surface ecosystems introduce variability through seasonal productivity cycles. In trenches, sedimentation often proceeds more steadily, allowing clearer interpretation of long-term environmental records preserved in sediment cores. Acoustic ecology emerges as another field of interest. Without light, sound becomes a primary communication channel for many organisms. Researchers deploy hydrophones to record ambient noise, biological signals, and geological activity. These recordings provide insights into ecosystem dynamics, tectonic movement, and even distant human activities such as shipping. Chemical sensing replaces vision for many species. Detecting dissolved organic compounds, nutrient gradients, or microbial activity allows organisms to locate food sources. Studying these sensory mechanisms helps scientists understand how life functions without reliance on light, expanding broader biological theory. Technological imaging continues improving despite darkness. Low-light cameras, intensified sensors, and advanced image processing algorithms enhance clarity. Combining multiple short exposures reduces noise. These innovations gradually improve visual documentation, though they cannot eliminate the fundamental limitation imposed by absence of sunlight. Human crews in submersibles sometimes describe the experience as surprisingly calm rather than frightening. The absence of visual clutter, combined with slow operational pace, creates a focused working environment. Still, awareness of the surrounding darkness never disappears completely. Training emphasizes procedural concentration to maintain safety and efficiency. Data interpretation often requires integrating multiple sensory inputs. Visual footage, sonar mapping, chemical sensors, temperature readings, and biological sampling all contribute pieces of the overall picture. No single data source provides complete understanding. Multidisciplinary analysis remains standard practice. Historical expeditions lacked modern imaging technology. Early researchers inferred conditions primarily from acoustic data and recovered samples. Modern expeditions build upon those foundations, refining interpretations with better instruments. The continuity of research highlights how scientific understanding evolves incrementally. Darkness influences corrosion processes as well. Lack of photosynthetic organisms reduces certain biofouling effects, though microbial activity still occurs. Material degradation patterns differ from shallower marine environments. Engineers consider these factors when selecting coatings and structural materials. Energy budgeting becomes critical for long-duration missions. Lighting, propulsion, data transmission, and sensor operation all draw from limited power reserves. Efficient system design extends mission duration and improves data collection opportunities. Psychological adaptation among researchers develops through experience. Initial exposure to deep-sea imagery may evoke unease, but repeated observation typically shifts focus towards scientific detail. Professional training encourages objective interpretation rather than emotional response. Public outreach often emphasises visual footage, even though it represents only a fraction of collected data. Communicating the reality of deep ocean darkness helps audiences appreciate exploration challenges. Educational programs sometimes simulate low-light conditions to demonstrate sensory limitations. As understanding of this perpetual darkness settles in, the environment of the Galathea Deep begins to feel less mysterious in a dramatic sense, more systematically analysable. Yet one more physical factor quietly shapes everything there as well, because alongside pressure and absence of light, the near-freezing temperatures of the abyss add another layer influencing biology, chemistry, and exploration logistics. Once darkness becomes familiar as a constant condition rather than something dramatic, attention often shifts naturally toward another quiet but very influential factor in the Galathea Deep environment, and that is temperature. Unlike surface oceans where warmth rises and falls with seasons, weather and sunlight exposure, the deepest parts of the ocean remain consistently cold. Not freezing solid, but very close to it. Typically, temperatures in abyssal trenches hover somewhere between 1 and 4 degrees Celsius. That narrow range does not fluctuate much, and this stability plays a surprisingly important role in how life survives and how scientific equipment operates down there. At first glance, cold water might not sound particularly remarkable. Many people experience cold weather on land regularly, but deep ocean cold differs in several ways. It is persistent, it is combined with extreme pressure, and it exists in total darkness. Those three factors together create a unique environment where physical, chemical and biological processes behave differently than in shallower seas. Surface waters near the Philippines can feel warm and comfortable, often exceeding 25 degrees Celsius. Sunlight heats the upper layers, winds mix them, and seasonal patterns shift temperatures gradually. Descending through the water column, however, a transition layer called the thermocline appears. In this region, temperature drops rapidly over a relatively short vertical distance. Beyond that layer, the water becomes cold and stays that way all the way down to the trench floor. This cold originates partly from polar regions. Dense, cold water forms near the poles and slowly sinks, then spreads across the deep ocean basins through global circulation patterns sometimes called thermohaline circulation. That process takes centuries. By the time the water reaches trenches like the Galathea Deep, it has travelled vast distances slowly, carrying dissolved gases, nutrients and subtle chemical signatures from faraway places. For scientists, stable temperature conditions provide both advantages and challenges. On one hand, consistent cold reduces certain types of environmental variability, making long-term measurements easier to interpret. Instruments do not experience rapid thermal cycling the way they might in shallower waters. On the other hand, cold temperatures affect battery efficiency, material flexibility, lubrication performance, and sensor calibration. Equipment must be designed specifically to function reliably near freezing. Battery chemistry becomes particularly important. Many conventional batteries lose capacity in cold environments because chemical reactions slow down. Deep-sea instruments often use specialized battery systems optimized for low-temperature operation. Even then, mission duration planning accounts carefully for reduced energy availability. Lubricants also behave differently. Fluids thicken in cold conditions, increasing mechanical resistance. Engineers select synthetic lubricants formulated to remain stable at low temperatures and under high pressure simultaneously. Failure to account for this can result in sluggish moving parts or complete mechanical seizure. Electronic components require thermal management as well. While cold can prolong the lifespan of some components, extreme cold combined with pressure can affect solder joints, connectors, and insulation materials. Designers sometimes incorporate slight internal heating to maintain stable operating conditions within instrument housings. From a biological perspective, cold temperatures slow metabolic rates. Organisms living in abyssal trenches often grow slowly, reproduce less frequently, and conserve energy efficiently. Food availability at such depths remains limited, so slower metabolism becomes advantageous. This contrasts sharply with many shallow water species where abundant sunlight supports faster biological cycles. Enzyme chemistry offers another fascinating adaptation. Enzymes in deep-sea organisms function effectively at low temperatures, where typical surface enzymes would operate sluggishly. Studying these enzymes provides insights into protein stability and catalytic efficiency. Industrial biotechnology occasionally draws inspiration from such systems when designing processes that must operate under cold conditions. Membrane structure in deep-sea organisms also reflects temperature adaptation. Cellular membranes must remain flexible enough to function despite cold. Specialized lipid compositions help maintain appropriate fluidity. Without these adaptations, cellular transport processes would become inefficient or fail entirely. Temperature stability influences chemical solubility as well. Cold water holds more dissolved gases, including carbon dioxide and oxygen, than warm water. This affects carbon cycling, respiration processes, and chemical equilibria within the trench environment. Understanding these dynamics contributes to broader climate science models. Sediment chemistry interacts with temperature in subtle ways. Organic matter decomposition proceeds more slowly in cold conditions, sometimes preserving materials longer than they would survive in warmer environments. Sediment cores extracted from deep trenches can therefore contain well-preserved biological and chemical records extending far back in time. Acoustic propagation changes slightly with temperature too. Sound speed varies depending on temperature, salinity and pressure. Sonar calibration accounts for these factors carefully to maintain mapping accuracy. Even small deviations can introduce measurement errors if not corrected. Human crews in submersibles do not feel the external cold directly because cabin environments remain controlled. Still, awareness of the surrounding near-freezing water contributes to the overall sense of operating in a distinctly different world. Equipment reliability becomes a constant focus precisely because environmental conditions remain unforgiving. Another interesting aspect involves microbial activity. Some deep-sea microorganisms remain active even near freezing temperatures, challenging earlier assumptions that metabolic processes would slow to near inactivity. These findings reshape understanding of biochemical limits and expand definitions of habitable environments. Climate change research increasingly considers deep ocean temperatures. While surface warming receives more attention, Heat absorption by deep waters influences long-term climate regulation. Monitoring abyssal temperature trends helps refine predictive models. Even slight changes at depth can indicate broader systemic shifts. Technological advances now allow long-term temperature logging at extreme depths. Autonomous sensor arrays can remain deployed for months or years, collecting continuous data. These records reveal subtle trends that short expeditions might miss. Data continuity strengthens scientific confidence in observed patterns. Public perception often associates deep ocean exploration primarily with pressure and darkness. Temperature receives less attention, yet it quietly shapes almost every process occurring there. Recognizing its importance helps create a more complete understanding of trench environments. Material durability under cold conditions also receives attention. Some polymers become brittle near freezing. Metals contract slightly, affecting tolerances. Composite materials require testing to ensure long-term resilience. Maintenance planning incorporates these factors explicitly. Energy transfer processes slow in cold water. Heat dissipates differently, affecting equipment, cooling systems. Designers sometimes rely on ambient cold water for passive thermal regulation, reducing the need for active cooling mechanisms. Biological diversity patterns correlate partly with temperature stability. Some species specialize narrowly for specific thermal ranges. Stable abyssal temperatures support unique ecological niches distinct from fluctuating surface ecosystems. As these temperature considerations settle into the overall picture, the environment of the Galathea Deep begins to feel less like a collection of isolated extremes and more like an integrated system where pressure, darkness and cold interact continuously. And once those physical conditions are understood together, curiosity naturally shifts toward how life manages to exist there at all. Because despite everything working against survival, organisms persist, adapt, and sometimes thrive in ways that still surprise researchers today. Once the cold stability of the abyss begins to make sense alongside the pressure and the darkness, the next piece of the picture often feels the most surprising. Life exists there. Not just microscopic traces, not occasional accidental visitors drifting down from above, but entire ecosystems built around conditions that seem, at first glance, completely unsuitable for complex biology. Scientists sometimes phrase it cautiously, saying that deep trench organisms challenge expectations rather than break natural laws. Still, the sense of surprise remains, because the Galathea Deep represents an environment where many traditional assumptions about habitability no longer apply in the straightforward way they do at the surface. For a long time, oceanographers suspected that extreme depths might host only sparse microbial life. Early theories suggested pressure, cold, lack of sunlight, and limited food supply would severely restrict biological complexity. That assumption started changing in the mid-20th century, when improved sampling techniques began retrieving organisms from increasingly deep environments. Each expedition added new evidence showing that life adapts more flexibly than previously believed. Food supply is often the first question people ask. Without sunlight, photosynthesis cannot occur, so the base of the food web must come from somewhere else. One major source involves organic material sinking slowly from surface waters. Tiny particles of dead plankton, fish waste, decaying plant material, and other debris drift downward continuously. Oceanographers sometimes refer to this steady fall as marine snow. It sounds gentle, and in a sense it is, but it represents a critical nutrient supply for deep ecosystems. Another food source comes from chemical processes independent of sunlight. Some microorganisms perform chemosynthesis, deriving energy from chemical reactions involving compounds like methane, hydrogen sulfide, or reduced minerals released from geological activity. This process supports small ecosystems even in complete darkness. While the Galathea Deep is not primarily known for hydrothermal vent systems, localized chemical gradients still exist and can support specialized microbial communities. Many deep trench organisms show structural adaptations related directly to pressure and food scarcity. Soft-bodied invertebrates, for example, often lack rigid skeletal structures that might collapse under pressure. Flexible tissues distribute mechanical stress more evenly. Some fish species exhibit reduced bone density combined with gelatinous tissue that maintains buoyancy without gas-filled organs. Eyes present an interesting case. Some species retain large, highly sensitive eyes capable of detecting faint, bioluminescent flashes from other organisms. Others lose functional vision entirely, relying instead on chemical sensing or vibration detection. Both strategies make sense depending on ecological niche. Maintaining visual organs requires energy, so if vision offers little advantage, evolutionary pressures favour reduction. Bioluminescence itself deserves attention. Many organisms produce light chemically through reactions involving specialised proteins and substrates. The emitted light serves multiple purposes. Predators use it to lure prey. Prey species deploy sudden flashes to startle attackers. Some organisms use patterned luminescence for communication, though understanding those signals remains an active research area. Scientists study these chemical systems partly for biomedical applications, including imaging techniques. Metabolism at abyssal depths tends to proceed slowly. Energy conservation becomes essential when food arrives unpredictably. Growth rates may be significantly slower than comparable species in shallow waters. Some organisms live longer lifespans relative to their size, reflecting reduced metabolic stress. These life history strategies challenge assumptions derived from more nutrient-rich environments. Microbial communities arguably represent the most abundant life forms in trenches. Piezophilic bacteria and archaea thrive under high pressure. Their cellular machinery stabilizes proteins and membranes in ways surface organisms cannot replicate easily. Research into these microbes informs biotechnology fields such as enzyme engineering, bioremediation, and pharmaceutical development. Reproductive strategies also adapt to environmental constraints. Some species release large numbers of offspring to increase survival probability in uncertain conditions. Others invest heavily in fewer offspring with higher individual survival chances. Observing reproductive behaviour remains difficult because direct observation opportunities are limited, but genetic studies and sampling provide indirect evidence. Chemical communication appears particularly important. Dissolved compounds travel effectively in deep water, allowing organisms to detect food sources, mates, or potential threats. Sensory adaptations include highly developed chemoreceptors capable of detecting minute concentration changes. These systems compensate for the absence of visual cues. Scavenger species often dominate visible fauna. Organic matter occasionally arrives in larger pieces, such as dead fish or marine mammals sinking from above. These events create temporary feeding opportunities, attracting diverse organisms. Time-lapse deep-sea camera deployments have documented such events, showing rapid congregation of scavengers despite overall sparse conditions. Symbiotic relationships occur as well. Some microorganisms live within larger host organisms, providing metabolic advantages such as nutrient processing. These partnerships illustrate how cooperative strategies enhance survival in resource-limited environments. Understanding symbiosis under extreme conditions informs broader ecological theory. Physiological research highlights protein stability mechanisms. High pressure tends to alter protein folding, potentially disrupting biological function. Deep-sea organisms produce stabilizing molecules that maintain proper structure. These biochemical strategies interest researchers exploring protein engineering for industrial processes. Membrane lipid composition again plays a central role. Maintaining appropriate membrane fluidity ensures nutrient transport, signal transduction, and cellular integrity. Specialized lipid molecules resist compression effects while preserving flexibility. Comparative studies between shallow and deep species reveal consistent patterns supporting these adaptations. Genetic analysis has accelerated discovery significantly. Environmental DNA sampling allows identification of organisms without direct capture. Sequencing trace genetic material from water samples reveals biodiversity previously undetectable through traditional methods. This technique continues expanding knowledge of deep trench ecosystems. Parasitic relationships also exist. Some organisms depend on hosts for nutrients, illustrating that even extreme environments support complex ecological interactions. Documenting these relationships requires careful sampling and molecular analysis. Evolutionary timescales matter greatly. Adaptations observed today reflect millions of years of gradual selection. Rapid environmental change could challenge these specialized organisms, which sometimes possess narrow tolerance ranges. Conservation considerations increasingly include deep-sea habitats as human activity expands into ocean resource extraction. Noise pollution from shipping and industrial activity can propagate to deep environments. While effects remain under study, acoustic disturbances may influence organism behavior. Understanding baseline ecological conditions helps evaluate potential impacts. Sampling challenges persist. Capturing organisms intact without pressure-induced damage requires specialized equipment. Pressure-retaining sampling containers allow laboratory study under near-natural conditions. These systems remain complex and expensive but provide invaluable biological insights. Public imagination sometimes gravitates toward unusual appearances of deep-sea creatures. Some species do look unfamiliar compared with surface fauna, yet most adaptations reflect practical survival strategies rather than novelty for its own sake. Scientists emphasize function over appearance when analyzing biological features. Energy efficiency emerges as a recurring theme. Every adaptation, from metabolism to sensory systems, reflects careful energy budgeting. In environments where food arrives unpredictably, efficiency determines survival. As this growing understanding of life at depth becomes clearer, the Galathea Deep begins to feel less like an empty void and more like a specialized ecosystem operating under different rules than surface environments. And with that realization in place, attention often turns toward another aspect. Researchers monitor closely, because alongside visible organisms there are also acoustic signals, subtle sounds travelling through the water that sometimes reveal activity before anything can be seen. Once the idea settles that life can exist even under crushing pressure, cold temperatures, and permanent darkness, another layer of the deep ocean environment begins to draw attention, and that is sound. In a place where light does not travel far and visibility remains limited, sound becomes one of the primary ways information moves through the water. Scientists studying regions like the Galathea Deep often rely more on acoustic data than visual observation, not because sound is more dramatic, but because it is simply more practical under those conditions. Water carries sound efficiently, much more efficiently than air, in fact. Vibrations travel faster and farther underwater, which means acoustic signals generated in one location can sometimes be detected at surprising distances. Researchers use this property deliberately. Sonar systems map the seafloor, acoustic beacons help guide submersibles, and hydrophones record environmental sounds continuously. These recordings become valuable data sets for understanding geological, biological, and even human-related activity in deep ocean environments. Natural geological sounds form one important category. The Philippine Trench, where the Galathea Deep sits, marks an active tectonic boundary. Plates shift slowly, occasionally producing earthquakes or minor tremors. Hydrophones placed at depth capture these movements as low-frequency acoustic signals. Studying them helps scientists track tectonic stress patterns and improve seismic hazard models. These acoustic records complement traditional seismographs, especially in regions where land-based monitoring stations remain sparse. Submarine landslides represent another acoustic source. Sediment accumulates on trench slopes over long periods. Occasionally, gravity, seismic activity, or fluid instability causes sudden downward movement. These events produce characteristic acoustic signatures detectable by sensitive instruments. Monitoring them contributes to understanding sediment transport and potential tsunami generation mechanisms. Biological sound production also occurs even in deep environments. Some marine organisms generate noises intentionally or incidentally. Fish may produce sounds through swim bladder vibrations or skeletal movements. Invertebrates sometimes create clicking or scraping noises while feeding or interacting. The overall soundscape tends to be quieter than shallow coastal waters, but it remains active enough to support ecological study. Bioluminescent organisms sometimes correlate with acoustic activity indirectly. Feeding events triggered by organic material falling from above may produce both light and sound. Time-synchronized recordings help researchers interpret ecological interactions that would otherwise remain hidden in darkness. Ambient ocean noise includes distant weather effects. Surface storms generate waves whose energy propagates downward acoustically. Hydrophones in deep trenches occasionally detect these signatures, allowing correlation between surface meteorological events and deep acoustic patterns. This connection provides additional data for ocean-atmosphere interaction studies. Human-generated sound has become increasingly noticeable. Commercial shipping, offshore industrial activity, and naval operations all contribute acoustic signals detectable at depth. Researchers analyze these signals both as potential environmental stressors and as practical calibration references. Understanding baseline noise levels helps distinguish natural sounds from anthropogenic sources. Communication with deep-sea equipment depends heavily on acoustics. Radio waves attenuate quickly in seawater, so acoustic modems transmit data between submersibles and surface vessels. Bandwidth remains limited compared with terrestrial wireless communication, but improvements continue steadily. Reliable acoustic communication supports real-time monitoring during missions. Sonar mapping remains one of the most consistent uses of sound in trench exploration. Multi-beam sonar systems emit acoustic pulses downward and measure return times. Converting those timings into depth measurements produces detailed bathymetric maps. Accuracy depends on correcting for temperature, salinity, and pressure effects on sound speed. Continuous calibration ensures reliable mapping results. Unexpected acoustic signals occasionally appear in recordings. Scientists approach these cautiously, first ruling out equipment artifacts or known environmental sources. In many cases, explanations emerge through further analysis. Rarely, unusual patterns prompt follow-up missions specifically to investigate their origin. This iterative process reflects standard scientific methodology rather than speculation. Acoustic ecology examines how organisms use sound for orientation, communication, or predator avoidance. While research in deep trenches remains limited compared with coastal ecosystems, evidence suggests some species rely on acoustic cues extensively. Understanding these behaviours contributes to broader ecological models. Long-term acoustic monitoring stations sometimes remain deployed for months or years. Autonomous recorders capture continuous data, later retrieved for analysis. These datasets reveal seasonal patterns, rare geological events, and gradual environmental changes not observable during short expeditions. Temperature and pressure influence sound propagation significantly. Sound speed increases with temperature and pressure, but decreases with salinity variations. Complex vertical sound channels can form, allowing signals to travel long distances with minimal attenuation. Oceanographers study these channels for both scientific and practical communication purposes. Equipment designed for acoustic monitoring must address pressure tolerance, corrosion resistance, and energy efficiency. Hydrophones require sensitive membranes protected from deformation. Data storage capacity must accommodate extended recording periods. Power management becomes critical for autonomous deployments. Signal processing techniques continue evolving. Advanced algorithms filter noise, identify patterns, and classify acoustic events automatically. Machine learning applications increasingly assist researchers in analysing large acoustic datasets that would otherwise require extensive manual review. Historical acoustic records sometimes provide retrospective insights. Comparing modern recordings with earlier data reveals trends in geological activity, shipping intensity, or biological presence. Such comparisons support long-term environmental assessment. Educational outreach often uses deep ocean sound recordings to illustrate unseen environments. Listening to acoustic data can make abstract scientific concepts more tangible. Public engagement through sound complements visual documentation, especially where imagery remains limited. Psychological responses to deep ocean sounds vary. Some recordings convey a sense of quiet punctuated by occasional distant events. Others capture continuous low-frequency background noise. Researchers typically interpret these sounds analytically rather than emotionally, focusing on data extraction. Policy discussions occasionally reference acoustic monitoring when considering marine conservation. Noise pollution impacts on marine life remain an active research topic. Establishing baseline acoustic conditions helps evaluate potential environmental changes. Technological crossover occurs here as well. Advances in underwater acoustics support submarine navigation, offshore infrastructure monitoring, and environmental assessment beyond purely scientific contexts. Shared technology development benefits multiple fields. Looking again at the Galathea Deep through this acoustic perspective, the environment becomes less silent than one might initially assume. Sound travels continuously, carrying information about geological movement, biological activity, and distant human presence. Researchers learn to interpret these signals carefully, adding another layer to understanding trench ecosystems. And as attention settles on how sound reveals activity where sight cannot, another practical challenge emerges naturally, because operating equipment in such an environment rarely proceeds without complications, and over time scientists have accumulated a number of experiences involving instrument malfunctions, lost probes, and the technical realities of working at extreme depths. Once sound becomes one of the primary ways scientists observe what cannot easily be seen, another practical reality of deep exploration starts to surface. And that is how often technology is pushed right to its limits. Exploration of the Galathea Deep and similar trenches depends almost entirely on equipment. Humans cannot simply descend there directly without extensive protection, and even robotic systems operate under constant stress. Over time, researchers have learned to expect occasional equipment failures. These events are rarely dramatic in a cinematic sense, but they remain an unavoidable part of working in environments defined by pressure, cold, darkness, and distance. Pressure alone accounts for many technical challenges. As depth increases, materials compress slightly even when engineered for strength. Seals that perform perfectly during laboratory testing sometimes behave differently after prolonged exposure to extreme conditions. Microscopic imperfections may expand under continuous stress. A pressure housing designed to protect sensitive electronics must remain flawless, because even a tiny leak can allow seawater intrusion, leading quickly to corrosion or electrical failure. Temperature compounds the situation. Near-freezing conditions affect battery performance, lubrication viscosity, and material flexibility. Mechanical joints may stiffen. Electrical connectors can contract subtly, altering contact reliability. Engineers account for these factors during design, but real-world environments still introduce unpredictable variables. Long-duration deployments especially reveal stresses that short laboratory simulations might miss. Communication limitations also contribute indirectly to equipment loss. Because radio waves do not travel effectively underwater, most deep-sea communication relies on acoustic signals. Bandwidth remains limited, and signal clarity can fluctuate due to environmental noise, temperature gradients, or terrain interference. If communication weakens or drops completely, operators sometimes must wait until recovery to determine equipment status. That delay complicates troubleshooting. Remotely operated vehicles, often tethered to surface ships, face particular challenges. Tethers provide power and data transmission, but introduce vulnerability. Strong currents, sharp geological features, or entanglement with debris can damage cables. When tether integrity is compromised, operators may have to release vehicles intentionally to avoid losing both the equipment and the ship connection. Recovery then becomes a separate operation requiring careful navigation. Autonomous underwater vehicles reduce tether risk but introduce other uncertainties. These vehicles follow pre-programmed routes, collecting data independently. If navigation systems malfunction or battery power depletes unexpectedly, locating the vehicle afterward can prove difficult. Acoustic beacons help track position, yet signal loss occasionally occurs. Recovery teams sometimes conduct extensive search operations to retrieve valuable instruments. Implosion events, while relatively rare, represent one of the most dramatic equipment failures. Pressure housing subjected to extreme compression can collapse suddenly if structural integrity is compromised. Engineers design safety margins precisely to prevent such outcomes, but no system remains entirely immune. Post-recovery analysis of failed components informs future design improvements. Corrosion presents another persistent concern. Saltwater acts as an effective electrolyte, accelerating electrochemical reactions that degrade metals. Protective coatings, sacrificial anodes, and corrosion-resistant alloys help mitigate this effect, yet long deployments still expose equipment to gradual wear. Maintenance schedules account for anticipated degradation, though unexpected variations occur. Biofouling sometimes affects instruments as well. Even at great depths, microorganisms colonize surfaces. Accumulated biological films can interfere with sensor readings, optical clarity, and mechanical movement. Designing anti-fouling surfaces and cleaning protocols becomes part of operational planning. Navigation errors occasionally contribute to equipment loss. Deep trenches contain uneven terrain, steep slopes, and loose sediments. Submersibles maneuver carefully, but visibility limitations mean reliance on sonar and navigation instruments. Small positional inaccuracies can lead to contact with terrain features. Protective frames reduce damage risk, yet incidents still occur. Funding realities also shape equipment management. Deep-sea instruments represent significant financial investment. Losses impact research budgets, sometimes delaying future missions. Insurance coverage exists for some operations, but not all. Institutions weigh scientific benefit against financial risk when planning expeditions. Training plays a central role in minimizing failure. Operators undergo extensive preparation, including simulator exercises replicating communication delays, equipment malfunction scenarios, and emergency procedures. Experience improves decision-making under uncertain conditions, reducing the likelihood of avoidable losses. Redundancy becomes standard practice. Critical systems often include backups, allowing continued operation even if primary components fail. Dual sensors, independent power supplies, and multiple communication channels increase reliability. Redundancy adds weight and cost, but improves mission success rates. Historical experience informs modern design significantly. Early expeditions sometimes underestimated environmental stresses. Lessons learned through trial and error contributed to today's more robust equipment standards. Documentation of failures forms a valuable engineering knowledge base. Recovery operations occasionally become scientific opportunities themselves. Retrieving a failed instrument allows detailed post-mortem analysis. Understanding failure mechanisms improves material science, structural engineering, and operational protocols. Each recovered probe contributes data beyond its intended measurements. Public perception sometimes interprets equipment loss as evidence of danger in a dramatic sense. Within scientific communities, such events are viewed more pragmatically. Complex technology operating in extreme environments inevitably encounters challenges. The focus remains on improving reliability rather than dramatizing setbacks. Environmental ethics influence recovery decisions. If retrieval poses ecological risk or requires excessive disturbance, scientists sometimes leave equipment in place. Advances in biodegradable materials and environmentally safe components help mitigate long-term impact in such cases. Insurance and risk assessment frameworks continue evolving. Institutions collaborate with insurers to establish realistic coverage models reflecting actual operational risk. These frameworks support sustained research despite occasional losses. Data preservation strategies also matter. Instruments often store data locally even when transmitting in real time. If communication fails late in a mission, physical recovery may still yield valuable information. Designing robust data storage systems protects scientific investment. Technological innovation often emerges directly from failure analysis. Stronger composites, improved seals, smarter navigation software, and more efficient power systems all trace part of their development history to earlier setbacks. Incremental improvement characterizes deep-sea engineering progress. International collaboration helps distribute risk. Shared expeditions pool resources and expertise, reducing individual institutional exposure. Joint ownership of equipment sometimes spreads financial responsibility as well. Educational training benefits from documented failure cases. Engineering students study real-world examples to understand design limitations. This knowledge transfer supports future innovation and safety. Looking again at the broader picture, equipment challenges do not discourage research. Instead, they reinforce careful planning, iterative design, and realistic expectations. Scientists accept that exploration at extreme depths involves uncertainty, yet the value of data collected often outweighs operational difficulties. And as these technical realities settle into place, attention often turns from equipment itself toward the human experience surrounding such exploration. Because even when researchers remain on the surface directing robotic missions, the psychological dimension of working with extreme, largely unseen environments continues to influence how science is conducted there. When equipment reliability, communication limits, and the sheer difficulty of operating at extreme depths become clear, attention often shifts quietly towards something less visible, but still very real. That is the psychological dimension of deep exploration. Scientists working with environments like the Galathea Deep usually remain physically safe aboard research vessels, yet the conditions they study can still influence mood, focus, and perception in subtle ways. Exploring places humans cannot directly experience in ordinary terms creates a different kind of mental landscape, one shaped by distance, uncertainty, and sustained concentration. One important factor involves the concept of remote presence. Most deep trench exploration relies on remotely operated vehicles, autonomous probes, or instrument arrays rather than direct human descent. Scientists observe data streams, acoustic readings, chemical measurements, and video feeds instead of experiencing the environment firsthand. This indirect interaction requires a mental adjustment. Researchers must translate abstract data into meaningful understanding without traditional sensory cues. Over time, training helps, but the process still demands sustained cognitive effort. Isolation plays a role as well, even though researchers are typically surrounded by colleagues on research vessels. Expeditions often last weeks or months. Ships operate far from land, communication with home remains limited, and daily routines revolve around scientific operations. These conditions create a unique working atmosphere. Some individuals find it calming and focused, while others require deliberate strategies to maintain mental balance. Sleep patterns sometimes shift during missions. Continuous operations mean work occurs around the clock in rotating shifts. Exposure to natural daylight can become irregular, particularly for teams monitoring nighttime instrument operations. Maintaining consistent sleep schedules requires planning, and fatigue management becomes part of expedition logistics. Institutions increasingly recognize that cognitive performance directly affects safety and data quality. Uncertainty also contributes to psychological complexity. Deep exploration rarely produces immediate clear answers. Instruments may behave unpredictably. Data may require extensive interpretation, and environmental conditions may delay planned activities. Scientists develop tolerance for ambiguity, but that tolerance is cultivated through experience rather than assumed automatically. Anticipation represents another subtle influence. Before deployments, teams invest significant preparation time. Equipment calibration, mission planning, funding coordination, and logistical arrangements build expectations. Waiting for results, especially when communication bandwidth is limited, can create a prolonged sense of suspense. Researchers learn patience as part of professional practice. Visual perception affects emotional response. Video feeds from extreme depths often show calm, slow-moving scenes. Darkness, sparse biological activity, and quiet geological landscapes produce a visual environment quite different from busy surface ecosystems. Some researchers describe the footage as meditative. Others find it slightly disorienting initially because familiar spatial references are absent. Sound recordings add another dimension. Acoustic monitoring sometimes produces continuous low-frequency background noise punctuated by occasional distinct signals. Interpreting these sounds analytically requires focus, but listening over extended periods can also create a distinctive mental atmosphere. Training emphasizes objective interpretation to prevent subjective impressions from influencing conclusions. Risk awareness remains present even when direct physical danger is minimal. Equipment represents significant investment, and mission success often depends on precise coordination. Awareness of potential failure encourages careful procedure adherence. This vigilance contributes to operational safety but requires sustained attention. Team dynamics become especially important during long expeditions. Interdisciplinary collaboration means individuals from different specialties share confined working spaces. Effective communication, mutual respect, and clear role definitions help maintain productive environments. Many institutions provide team-building training specifically for field research contexts. Technological mediation shapes experience. Scientists interact with computer interfaces, control consoles, and data visualization tools extensively. This mediated environment differs from traditional fieldwork involving direct environmental contact. Some researchers appreciate the analytical clarity it provides. Others occasionally miss sensory engagement typical of terrestrial field studies. Emotional attachment to research sites sometimes develops gradually. Repeated expeditions to the same trench foster familiarity. Scientists begin recognizing patterns in data, seasonal variations, and long-term trends. This familiarity enhances interpretive accuracy but also introduces a sense of connection to a place most people will never see. Historical awareness contributes as well, knowing that previous generations of researchers worked with less advanced equipment can create perspective. Modern scientists build upon decades of accumulated knowledge. This continuity reinforces professional identity and purpose. Educational outreach often involves sharing psychological aspects alongside scientific findings. Students considering oceanography careers benefit from realistic expectations about fieldwork conditions. Understanding both rewards and challenges supports informed career decisions. Coping strategies vary among individuals. Some maintain personal routines such as exercise, reading, or structured downtime during expeditions. Others rely on social interaction with colleagues. Institutions increasingly recognize mental well-being as integral to scientific productivity. Data analysis phases sometimes present their own psychological patterns. Large data sets require prolonged concentration. Interpreting ambiguous results demands patience. Breakthrough moments occur, but they typically follow extended incremental work rather than sudden insight. Public perception sometimes emphasizes adventure narratives. While exploration does involve logistical challenges, the daily reality usually centers on systematic observation, calibration, documentation, and analysis. Communicating this balanced perspective helps manage expectations. Ethical considerations occasionally intersect with psychological factors. Researchers remain aware of environmental impact. Minimizing disturbance while maximizing knowledge requires thoughtful decision-making. This responsibility reinforces professional standards. Funding uncertainty can influence morale. Research grants often operate on multi-year cycles. Continuity of projects depends partly on successful proposals. Institutions support researchers through administrative assistance, yet uncertainty remains inherent to scientific careers. Technological reliability affects confidence. Well-designed equipment fosters trust, allowing scientists to focus on interpretation rather than troubleshooting. Conversely, repeated technical issues may require additional attention, influencing workflow dynamics. Interdisciplinary dialogue enriches perspective. Conversations between geologists, biologists, chemists, and engineers broaden understanding of complex systems. Such collaboration enhances both scientific outcomes and professional satisfaction. Long-term commitment to deep-sea research often reflects intrinsic curiosity. Scientists choose this field knowing its challenges. Sustained motivation typically arises from interest in unanswered questions rather than external recognition alone. As these psychological elements settle into place, deep exploration begins to feel less like a distant technical exercise and more like a human endeavour shaped by curiosity, patience, teamwork, and adaptation. And once that human dimension becomes clear, attention naturally shifts again toward the environment itself, particularly the geological forces operating beneath the trench, because tectonic activity continues shaping conditions there in ways that influence everything from sediment distribution to seismic risk. When the human side of deep exploration becomes clearer, attention often shifts back toward the environment itself, especially the geological forces operating beneath places like the Galathea Deep. This trench does not exist as a static feature carved once and left unchanged. It sits along a tectonic boundary where Earth's crust is in slow but constant motion. That motion is not always dramatic or immediately noticeable, yet over long time scales it shapes the trench, influences ocean chemistry, and contributes to seismic activity affecting surrounding regions. The Philippine Trench forms where one tectonic plate gradually moves beneath another in a process called subduction. The Philippine Sea Plate descends beneath the complex set of smaller plates and microplates, making up the Philippine Mobile Belt. This movement occurs at a rate measured in centimetres per year, which sounds slow, but across thousands or millions of years it produces significant geological change. Trenches deepen, sediments accumulate, and stress builds along fault zones. Subduction zones represent some of the most geologically active regions on the planet. Earthquakes occur as accumulated stress releases suddenly along fault lines. Most of these events remain small and go unnoticed outside scientific monitoring networks. Yet occasional larger events can influence coastal communities through ground shaking or tsunami risk. Continuous monitoring helps scientists refine hazard assessments. Seafloor mapping reveals that the trench floor is not a smooth depression. Instead, it contains ridges, slopes, fractured rock formations, and thick sediment layers. Geological surveys using sonar and seismic imaging show complex structures formed by tectonic compression, sediment deposition, and occasional submarine landslides. These landslides sometimes produce acoustic signals detectable by hydrophones, linking geological activity with the acoustic environment scientists monitor. Sediment behaviour plays a central role in trench evolution. Material arriving from continental margins, volcanic eruptions, and biological productivity gradually accumulates along trench walls and floor. Pressure compacts these sediments over time, altering their physical properties. Fluid trapped within sediment layers can migrate slowly, influencing stability. Under certain conditions, sediment layers may slip, contributing to slope instability. Fluid dynamics beneath the seafloor add further complexity. Subduction zones often host fluid release from descending plates. Water trapped in minerals within the subducting crust can be released as pressure and temperature increase. These fluids migrate upward, affecting rock strength, fault lubrication, and chemical composition of surrounding water. Studying fluid movement helps explain earthquake behavior and mineral formation processes. Temperature gradients exist beneath the seafloor despite the cold ocean water above. Geological heat flow from Earth's interior influences rock properties and fluid movement. Heat flow measurements in trench regions contribute to understanding plate tectonics and mantle convection patterns. These measurements require specialized probes capable of functioning under high pressure. Volcanic arcs sometimes develop parallel to trenches where subduction occurs. While the Galathea Deep itself is not a volcanic vent site, its geological setting connects to broader tectonic systems that include volcanic activity elsewhere in the region. Understanding these connections supports integrated models of regional geology. Seismic monitoring involves both land-based stations and ocean-bottom seismometers. Deploying instruments on the seafloor presents logistical challenges but provides valuable data unavailable from land stations alone. Ocean-bottom instruments capture subtle seismic signals, improving event localization accuracy and helping scientists understand stress distribution along plate boundaries. Tsunami research frequently incorporates trench data. Large undersea earthquakes can displace water masses, generating waves that travel long distances. Understanding trench geometry, sediment stability, and fault characteristics improves tsunami modelling. Coastal warning systems depend partly on this research. Chemical interactions between seawater and newly exposed rock surfaces occur continuously in tectonically active regions. Mineral dissolution, precipitation, and fluid exchange influence water chemistry. Sampling water and sediments near the trench helps geochemists track these processes. Geophysical imaging techniques have advanced considerably. Reflection, seismic surveys, gravity measurements, and magnetic field mapping all contribute to understanding subsurface structures. Integrating these data sets produces three-dimensional models of trench geology. Continuous refinement occurs as new data becomes available. Historical earthquake records combined with geological evidence provide context for long-term activity patterns. Sediment layers sometimes contain traces of past seismic events, such as disturbed strata or unusual deposits. Interpreting these records helps estimate recurrence intervals for significant earthquakes. Engineering considerations for deep-sea infrastructure also rely on geological stability assessments. While permanent installations in trenches remain rare, cable routes, monitoring stations, and scientific observatories sometimes approach tectonically active areas. Understanding geological risk informs design decisions. International collaboration remains essential in tectonic research. Plate boundaries extend across national jurisdictions. Shared data improves regional hazard assessments and scientific understanding. Collaborative expeditions often focus on comprehensive geological surveys. Educational outreach sometimes emphasizes tectonic processes because they illustrate Earth's dynamic nature clearly. Trenches provide tangible examples of plate interaction. Public understanding of these processes supports disaster preparedness initiatives in coastal regions. Biological communities sometimes respond to geological changes. Sediment disturbance can alter habitat structure. Fluid seepage may create localized chemical environments supporting specialized organisms. Interdisciplinary research examines these interactions between geology and biology. Technological resilience remains a constant concern. Equipment deployed near tectonic boundaries must tolerate potential seismic disturbance. Flexible mooring systems, shock-resistant housings, and redundant data storage help protect scientific instruments. Climate research intersects with geological study in subtle ways. Subduction processes influence long-term carbon cycling, by transporting carbon-bearing sediments into Earth's interior. Understanding these mechanisms contributes to global carbon budget models. Data analysis increasingly incorporates computational modelling. Simulations of plate movement, sediment transport and fluid flow complement field observations. Model validation depends on accurate trench measurements. Public perception sometimes associates tectonic instability with immediate danger. In practice, most geological processes occur gradually. Continuous monitoring provides early detection of significant changes, allowing informed response planning. Professional training for marine geologists includes both field experience and advanced analytical techniques. Familiarity with trench environments enhances interpretive accuracy. Experience builds confidence in data evaluation. Policy implications extend to coastal development, disaster planning, and environmental management. Scientific findings inform government decisions related to infrastructure, evacuation planning, and resource management. As geological instability becomes better understood, the Galathea Deep appears less like a static abyss and more like an evolving feature shaped by ongoing tectonic processes. This perspective reinforces the importance of continued observation, and once geological dynamics settle into the broader understanding of the trench, attention often moves again toward what remains unknown there. Because even with improved mapping, monitoring and modelling, many aspects of the ecosystem, chemistry and physical processes continue to elude complete explanation. When geological activity becomes clearer as a slow but persistent force shaping the Galathea Deep, the conversation often turns naturally towards something equally important yet less visible, and that is the possibility of entire ecosystems still hidden from observation. Even after decades of oceanographic research, scientists remain careful when describing what is known about deep trench biology. The simple reason is that direct sampling remains limited, and the environment makes observation difficult enough that absence of evidence rarely means evidence of absence. Much of what exists there is inferred from partial data rather than continuous monitoring. One reason hidden ecosystems remain plausible involves sheer spatial scale. Trenches are not uniform depressions with flat floors. They contain ridges, slopes, sediment pockets, fractured rock zones, and chemical microenvironments. Each of these features can support distinct biological communities. Sampling a few locations provides valuable insight, yet it does not guarantee complete coverage. Researchers therefore treat each expedition as an incremental expansion of the knowledge rather than a comprehensive survey. Chemical gradients often drive ecosystem specialization. Even small variations in dissolved minerals, organic matter concentration, or fluid seepage can create microhabitats suitable for particular organisms. Some bacteria thrive in areas with elevated methane levels. Others prefer mineral-rich seep zones. Mapping these gradients precisely requires extensive sensor deployment, which takes time and resources. Sediment layers add another dimension. Organic material settling from surface waters accumulates unevenly. Certain depressions collect more debris, supporting higher microbial productivity. These localized nutrient hotspots can attract larger organisms intermittently. Time-lapse observations show that feeding events sometimes occur unpredictably, complicating ecological modelling. Microbial diversity likely exceeds current cataloguing significantly. Environmental DNA sampling has revealed genetic sequences that do not match known species. These findings suggest undiscovered microorganisms adapted specifically to extreme trench conditions. Culturing such organisms in laboratories remains challenging because replicating pressure, temperature and chemical conditions simultaneously requires specialized equipment. Symbiotic relationships represent another area of incomplete knowledge. Some deep-sea organisms may depend on microbial partners for nutrient processing. These associations can remain hidden unless detailed molecular analysis is performed. Advances in genomic sequencing continue improving detection capability, gradually revealing more complex ecological networks. Energy sources beyond surface-derived organic matter remain an active research topic. Chemosynthetic pathways, though better documented near hydrothermal vents, may operate at lower intensity in trench environments through mineral-water interactions. Identifying these processes requires sensitive chemical analysis combined with biological sampling. Temporal variability complicates ecosystem assessment. Deep trenches appear stable, yet episodic events such as sediment slides, organic falls, or tectonic disturbances can reshape habitats suddenly. Short expeditions may miss these events entirely. Long-term monitoring equipment helps, but coverage remains incomplete. Visual observation challenges persist. Even high-resolution cameras illuminate limited areas. Organisms adapted to darkness may avoid bright artificial lights, further reducing detection probability. Researchers sometimes use low-light imaging systems to minimize disturbance, though image clarity decreases accordingly. Acoustic monitoring occasionally hints at biological activity not yet visually confirmed. Certain sound patterns suggest organism movement or interaction, but without corresponding visual data interpretation remains cautious. Integrating acoustic and visual datasets continues improving understanding gradually. Food web structure in trenches remains partially understood. Primary productivity relies largely on organic matter sinking from above, but precise energy transfer pathways between microbial communities, invertebrates, and larger organisms require further study. Stable isotope analysis provides clues, yet comprehensive models remain under development. Population dynamics also remain uncertain. Growth rates, reproduction cycles, and mortality patterns differ from shallow water species. Slow metabolism implies longer lifespans for some organisms, but confirming this requires extended observation periods rarely achievable during standard expeditions. Geographical isolation contributes to potential biodiversity uniqueness. Trenches separated by large ocean distances may host distinct species evolved independently. Comparative studies between trenches like the Mariana, Tonga, and Philippine systems suggest both similarities and localized differences. Climate change introduces additional uncertainty. Alterations in surface productivity, ocean circulation, and temperature profiles could influence organic matter flux to deep trenches. Predicting ecological responses requires baseline data still being assembled. Technological advances offer new opportunities. Autonomous vehicles equipped with environmental DNA samplers, chemical sensors, and imaging systems can cover larger areas than traditional tethered vehicles. Data integration from multiple platforms improves ecosystem mapping accuracy. Ethical considerations shape exploration methods. Minimizing habitat disturbance while maximizing knowledge requires careful planning. Non-invasive observation techniques receive increasing emphasis, though they sometimes limit sample availability. Funding constraints influence research pace. Comprehensive ecosystem mapping demands sustained investment. Collaborative international projects help distribute costs, yet priorities must be balanced across many marine research objectives. Educational initiatives encourage interdisciplinary training. Future ocean scientists increasingly combine biology, chemistry, geology, and data science expertise. Complex ecosystems require integrated analytical approaches. Public engagement occasionally highlights newly discovered species, sparking interest in deep-sea conservation. While media coverage often focuses on unusual appearances, scientists emphasize ecological function and environmental context. Policy discussions increasingly include deep-sea habitats. Potential resource extraction, cable routing, and climate mitigation strategies intersect with trench ecosystems. Scientific understanding informs regulatory frameworks. Data management becomes critical as sampling expands. Large genomic data sets, chemical measurements, acoustic recordings, and visual archives require coordinated storage and analysis infrastructure. Open data initiatives support broader collaboration. Comparative ecosystem studies benefit from standardized sampling protocols. Consistency improves cross-trench comparisons, strengthening ecological conclusions. Historical context remains valuable. Early expeditions provided baseline observations. Comparing modern data with historical records reveals long-term trends, though methodological differences require careful adjustment. Interdisciplinary workshops often focus specifically on unknown trench ecosystems. Collaborative discussion accelerates hypothesis development and research planning. Technological simulation tools allow virtual ecosystem modeling. These models guide expedition design by highlighting priority sampling areas. As awareness grows that unknown ecosystems likely persist within the Galathea Deep, the trench begins to feel less like a singular extreme environment and more like a mosaic of specialized habitats still under exploration. This perspective reinforces the importance of continued research. And with that understanding in place, attention often shifts toward how this trench compares with others studied more extensively, because placing the Galathea Deep alongside better-known trenches helps clarify both its uniqueness and its shared characteristics within the broader system of Earth's deepest ocean features. Once the possibility of hidden ecosystems begins to feel realistic rather than speculative, the next step that scientists often take is comparison. No trench exists in isolation when it comes to understanding deep ocean systems. Each one forms part of a broader network shaped by plate tectonics, ocean circulation, sediment transport, and biological adaptation. Comparing the Galathea Deep with other trenches does not diminish its uniqueness. Instead, it helps clarify what features are typical of deep trenches and what characteristics appear more specific to its location within the Philippine Trench system. The Mariana Trench usually receives the most public attention because it contains the deepest confirmed point on Earth, the Challenger Deep. Its depth slightly exceeds that of the Galathea Deep. This difference, however, does not make the Philippine Trench less scientifically interesting. Depth alone rarely determines research value. Geological setting, chemical environment, sediment composition, and biological communities all contribute important distinctions. Geologically, both trenches arise from subduction processes, yet the plates involved differ. The Mariana Trench forms where the Pacific Plate descends beneath the Mariana Plate. The Philippine Trench reflects interaction between the Philippine Sea Plate and the Philippine Mobile Belt. These differences influence seismic activity patterns, volcanic arc development, and crustal composition. Comparative tectonic studies help scientists refine plate movement models across the Western Pacific. Sediment characteristics vary as well. Some trenches accumulate thick sediment layers derived from nearby continental margins or volcanic activity. Others remain relatively sediment-poor due to current patterns or geological barriers. Sediment composition influences chemical cycling, microbial activity, and slope stability. Sampling across multiple trenches allows researchers to identify consistent patterns in local anomalies. Water chemistry differences also vary. Dissolved oxygen levels, nutrient concentrations and trace metal content depend partly on regional circulation. Deep water masses travelling from polar regions mix differently in each basin. Comparing chemical profiles helps oceanographers understand large-scale circulation pathways and their ecological consequences. Biological diversity comparisons reveal both shared adaptations and unique species. Pressure tolerance mechanisms appear broadly similar across trenches. Soft-bodied structures, specialised membranes and slow metabolism occur frequently. Yet genetic studies increasingly show distinct evolutionary lineages isolated by geographic separation. This isolation encourages speciation, contributing to global marine biodiversity. Hydrothermal activity represents another comparison point. Some trenches lie near active vent systems releasing mineral-rich fluids. These environments support chemosynthetic ecosystems independent of surface-derived nutrients. The Galathea Deep does not host major hydrothermal vent fields in the same way certain Pacific ridge systems do, though localized chemical seepage still occurs. Distinguishing these conditions helps interpret biological energy sources. Acoustic environments differ subtly between trenches. Geological activity, sediment movement, and biological populations all influence ambient sound profiles. Comparative acoustic monitoring assists both ecological research and seismic hazard assessment. Long-term hydrophone deployments across multiple trenches contribute valuable data sets. Temperature stability remains broadly similar among deep trenches, generally near freezing. However, slight variations occur depending on regional water mass origin and circulation patterns. These differences can influence species distribution and chemical reaction rates. Exploration history varies significantly. The Mariana Trench has seen more crude descents and high-profile expeditions, partly due to its record depth status. The Philippine Trench, including the Galathea Deep, has received steady scientific attention but less public visibility. Research output remains substantial, even if media coverage differs. Technological deployment strategies sometimes reflect these historical differences. Equipment proven in one trench may be adapted for use in another. Engineers learn from cross-site experience, improving reliability across deep-sea exploration programs. Ecological productivity varies as well. Trenches receiving greater organic input from surface waters may support denser biological communities. Regional climate patterns, upwelling systems, and surface productivity influence this input. Comparative biological sampling helps clarify energy flow dynamics. Plate movement rates differ across subduction zones. Faster convergence rates may correlate with increased seismic activity or sediment disturbance frequency. Monitoring multiple trenches helps refine these relationships. Geochemical cycling comparisons contribute to climate research. Trenches act as long-term carbon sinks through sediment burial. Understanding burial rates across different trenches informs global carbon budget models. Policy considerations sometimes emerge from comparative research. Conservation priorities may focus on trenches hosting unique biodiversity or sensitive geological features. International collaboration becomes essential because trenches often span multiple jurisdictions. Educational outreach benefits from comparison as well. Explaining similarities and differences between trenches helps audiences grasp broader oceanographic principles without focusing solely on one location. Data standardization initiatives support comparative studies. Consistent sampling protocols improve reliability when analysing cross-trench data sets. International organisations encourage methodological alignment. Remote sensing techniques continue evolving. Satellite altimetry combined with sonar mapping enhances comparative bathymetric models. Improved resolution reveals subtle structural differences previously undetectable. Interdisciplinary conferences frequently address trench comparison specifically. Researchers share findings, discuss methodological challenges, and plan collaborative projects. These interactions accelerate scientific progress. Historical data integration remains valuable. Early expeditions to different trenches produced varied measurement quality. Modern reanalysis helps align these data sets for meaningful comparison. Public perception sometimes simplifies trenches into a single category of very deep places. Scientific comparison reveals much richer diversity in geological structure, ecology, and chemical environment. Technological innovation often benefits from cross-trench testing. Equipment validated in one extreme environment typically performs reliably in others with similar conditions. Looking again at the Galathea Deep within this broader comparative framework, it becomes clear that while it shares fundamental characteristics with other trenches, its specific tectonic context, sediment dynamics, and biological potential justify continued focused study. And once those comparisons settle into place, attention tends to shift naturally toward the remaining uncertainties themselves, because even after decades of exploration, many questions about the trench persist, shaping ongoing research priorities and scientific curiosity alike. When comparisons with other trenches begin to provide context, it becomes clear that understanding the Galathea Deep has advanced steadily. Yet an equally important part of the story involves the limits of current knowledge. Scientists often speak carefully about what remains uncertain, not because research has stalled, but because deep ocean environments reveal complexity faster than they can be fully explained. Acknowledging what is not yet understood helps guide future studies and prevents assumptions from hardening into premature conclusions. One of the most fundamental unknowns involves biodiversity. Even with environmental DNA sampling, remotely operated vehicles and improved imaging systems, only a small fraction of the trench ecosystem has likely been documented directly. Many microorganisms remain uncultured in laboratory conditions. Some larger organisms may exist in low population densities or occupy habitats not yet sampled. Because sampling coverage remains incomplete, scientists avoid making definitive claims about total species diversity. Food web dynamics represent another open question. While sinking organic material from surface waters provides a recognised energy source, the exact pathways through which nutrients move between microbial communities, invertebrates, and higher organisms are still being mapped. Chemosynthetic processes may contribute more than previously assumed, but quantifying their role requires additional chemical and biological measurements. Establishing complete energy budgets remains an ongoing effort. Geochemical cycling at extreme depth also retains uncertainties. Carbon storage mechanisms, methane dynamics, and mineral-water interactions operate under high pressure and low temperature simultaneously. Laboratory simulations approximate these conditions, yet real trench environments introduce complexities difficult to replicate precisely. Field data continues refining theoretical models, though gaps remain. Seismic behaviour within the Philippine Trench raises further questions. Plate movement rates, fault lubrication by fluids, and sediment stability all influence earthquake characteristics. Monitoring networks have improved, but understanding long-term patterns still requires extended data sets spanning decades or longer. Researchers continue integrating geological, acoustic and geophysical observations to clarify these relationships. Sediment accumulation rates vary spatially within the trench, determining how quickly layers build up, how often landslides occur, and how sediments interact with tectonic processes remains an active research topic. Sediment cores provide historical snapshots, yet coverage remains geographically uneven. Hydrodynamic circulation patterns at extreme depth present another area of ongoing investigation. Deep currents influence nutrient distribution, sediment transport, and temperature stability. Measuring these currents accurately requires long-term sensor deployments, which face logistical and financial constraints. Acoustic ecology remains partly unexplored. Hydrophone recordings capture environmental sounds continuously, but distinguishing biological signals from geological or anthropogenic noise requires advanced signal processing. Understanding how organisms use sound in complete darkness continues evolving as analysis techniques improve. Pressure-related biological adaptation still holds unanswered biochemical questions. Researchers know that certain proteins and membranes function effectively under extreme compression, yet the molecular mechanisms underlying this stability remain under detailed study. Insights from this research may influence biotechnology applications, but translating findings into practical use takes time. Reproductive strategies of deep trench organisms also remain only partially documented. Observing breeding behavior directly proves difficult due to environmental constraints. Genetic analysis suggests certain patterns, yet comprehensive life cycle data remains limited. Climate change impacts on abyssal trenches represent another emerging area of uncertainty. Surface ocean warming, altered productivity, and shifting circulation patterns could influence deep ecosystems indirectly. Detecting these effects requires baseline data still being assembled. Chemical pollution transport to deep trenches has begun attracting attention. Microplastics, industrial contaminants, and persistent organic pollutants have been detected in some deep-sea environments. Understanding distribution pathways, ecological impact, and long-term accumulation trends requires further study. Technological limitations continue shaping knowledge boundaries. Instrument endurance, communication bandwidth, and energy storage capacity all influence how much data can be collected during each mission. Advances occur steadily, yet exploration pace remains incremental. Geophysical modelling benefits from trench data, but uncertainties persist regarding mantle convection interactions and long-term tectonic evolution. Integrating deep ocean observations with global geological models remains a complex undertaking. Microbial metabolic diversity likely exceeds current characterization. Genetic sequencing reveals unknown metabolic pathways whose ecological significance is still being determined. Culturing these organisms under realistic pressure conditions remains technically challenging. Symbiotic relationships among trench organisms represent another area of limited understanding. Molecular analysis suggests complex interactions, but direct observation remains rare. Clarifying these relationships contributes to broader ecological theory. Long-term ecological stability versus variability remains under investigation. Some evidence suggests trench environments change slowly, yet episodic events such as sediment slides or organic falls introduce variability. Quantifying this balance requires sustained monitoring. Policy implications intersect with scientific uncertainty. Resource exploration, conservation planning, and infrastructure development depend on reliable environmental data. Continued research helps inform responsible decision-making. Educational outreach increasingly emphasizes uncertainty as a natural part of science. understanding that unanswered questions drive research, encourages public support for continued exploration. Funding priorities sometimes shift as new questions emerge. Balancing immediate research goals with long-term monitoring needs requires strategic planning within scientific institutions. Interdisciplinary collaboration helps address knowledge gaps. Combining geological, biological, chemical, and physical oceanography expertise improves interpretive accuracy. Historical context remains valuable when assessing unknowns. Early expeditions established baseline measurements that modern research continues refining. Data integration across trenches improves comparative understanding. Shared databases support broader analysis beyond individual expedition findings. Technological innovation often arises specifically to address persistent unknowns. Improved sensors, autonomous platforms, and analytical techniques expand observational capability. As awareness of these remaining uncertainties settles in, the Galathea Deep appears not as a solved mystery, but as an ongoing scientific frontier where each answer tends to generate additional questions. This perspective keeps research momentum steady. And with that recognition in place, attention naturally begins shifting toward how exploration methods themselves continue evolving, because future technology will likely shape how quickly and thoroughly these remaining unknowns can be investigated. When the unanswered questions begin to stack up clearly enough, the conversation often moves toward how researchers actually plan to address them, because understanding what remains unknown naturally leads to discussion about future exploration. Deep-sea science has always advanced in close partnership with technology. Each generation of instruments expands observational reach slightly farther, improves data quality, or reduces operational risk. The Galathea Deep, like many extreme marine environments, stands as a testing ground for these evolving tools, and the next phase of exploration will likely look quite different from the expeditions that first identified the trench decades ago. Autonomous underwater vehicles are already playing a central role in this shift. Earlier exploration depended heavily on tethered, remotely operated vehicles connected directly to research ships. Those systems remain valuable, especially when real-time control is essential, but autonomy extends operational flexibility. Modern autonomous vehicles can follow pre-programmed routes, adjust behavior based on environmental conditions, and remain submerged for extended periods without constant supervision. Improvements in battery density and power management continue increasing mission duration, allowing broader spatial coverage during a single deployment. Artificial intelligence integration represents another emerging development. Machine learning algorithms now assist in interpreting sonar data, identifying geological structures, classifying biological imagery, and filtering acoustic recordings. Instead of scientists manually reviewing every data point, automated systems highlight patterns requiring closer attention. This approach accelerates analysis while still relying on human expertise for interpretation. The balance between automation and expert oversight continues evolving as algorithms improve. Communication technology remains an area of active development. Acoustic modems currently dominate deep-sea data transmission, but bandwidth limitations persist. Research groups are experimenting with hybrid communication methods, including optical systems for short-range, high-speed transmission combined with acoustic links for long-distance signaling. These advances could allow more real-time monitoring, reducing delays between data collection and analysis. Materials science contributes quietly but significantly. Pressure-resistant composites, corrosion-resistant alloys, and improved sealing technologies extend equipment lifespan and reliability. Lightweight yet strong materials reduce energy requirements for propulsion and deployment. These incremental engineering improvements collectively enhance mission efficiency. Energy systems remain critical. Battery technology advances, often driven by terrestrial applications such as electric vehicles, translate into longer underwater mission capability. Researchers are also exploring alternative energy harvesting methods, including ocean current turbines and thermal gradient converters, to power long-term monitoring stations without frequent retrieval. Sensor technology continues expanding. Modern instruments measure temperature, salinity, pressure, dissolved gases, trace metals, organic compounds, and microbial genetic material simultaneously. Miniaturization allows multiple sensors to operate on a single platform, increasing data richness without significantly increasing deployment complexity. Imaging systems are improving steadily as well. Low-light cameras, enhanced image stabilization, and advanced post-processing algorithms produce clearer visuals despite environmental constraints. Three-dimensional mapping techniques combine sonar and optical data to generate detailed terrain reconstructions. Environmental DNA sampling stands out as a particularly promising method. Instead of capturing organisms physically, scientists collect water samples containing genetic traces shared by organisms. Sequencing this DNA reveals biodiversity patterns even when direct observation proves difficult. Continued refinement of this technique could transform biological surveys in deep trenches. Long-term observatory networks represent another direction for future exploration. Permanent or semi-permanent instrument arrays placed on the seafloor can monitor environmental conditions continuously for years. These observatories track temperature trends, seismic activity, chemical changes and biological presence over extended periods, providing data sets impossible to obtain through short expeditions alone. Robotic maintenance capability may eventually support these observatories. Autonomous service vehicles could replace batteries, recalibrate sensors, or retrieve data modules without requiring full research vessel deployment. Early prototypes already exist, though widespread implementation remains in development. Human-crewed submersibles will likely remain part of exploration programs, though their role may evolve. Crewed missions provide direct observation and rapid decision-making advantages that autonomous systems cannot fully replicate. However, safety considerations, cost and endurance limits mean robotic systems will continue handling most routine surveys. Data management infrastructure is becoming increasingly important. Massive data sets generated by modern instruments require advanced storage, processing and sharing frameworks. Cloud computing, distributed databases, and open-access scientific repositories support collaborative analysis across institutions and countries. International cooperation will likely intensify. Deep sea exploration benefits from shared resources, expertise, and standardized methodologies. Multinational expeditions reduce duplication of effort and expand geographic coverage. Policy frameworks encouraging data sharing continue developing. Environmental stewardship considerations are gaining prominence. As technological capability grows, ensuring minimal ecological disturbance becomes a priority. Non-invasive observation techniques, biodegradable materials, and careful mission planning help balance exploration with conservation. Educational initiatives are adapting alongside technological change. Training future ocean scientists increasingly includes robotics, data science, genomics, and interdisciplinary collaboration skills. This broadened skill set reflects the complexity of modern marine research. Commercial interest in deep-sea resources sometimes intersects with scientific exploration. mineral prospecting, telecommunications infrastructure, and environmental monitoring all benefit from improved deep-sea technology. Coordinating scientific and commercial objectives responsibly requires clear regulatory frameworks. Public engagement continues influencing funding priorities. Documentaries, virtual reality experiences, and interactive educational programs help audiences understand deep-sea research relevance. Increased awareness often translates into broader support for sustained exploration funding. Climate science applications remain a strong driver. Understanding deep ocean heat absorption, carbon storage, and circulation patterns informs global climate models. Continuous monitoring helps detect long-term environmental trends. Space exploration analogies occasionally emerge. Techniques developed for deep-sea robotics sometimes inform planetary exploration systems, and vice versa. Both environments require remote operation under extreme conditions. Ethical discussions about exploration impact are expanding. Scientists increasingly consider not only data collection goals, but also long-term ecological consequences. Responsible exploration frameworks emphasize precautionary principles. Looking ahead, exploration of places like the Galathea Deep will likely become more continuous rather than episodic. Instead of isolated expeditions separated by years, persistent monitoring networks may provide ongoing observation. This shift would transform understanding from snapshot-based to process-based. And as future exploration methods begin to take shape in that way, attention often turns back toward the human response to all this knowledge. Because even as technology advances and data accumulates, there remains something distinctly personal about how people react to the idea of such vast, largely unseen environments beneath the ocean's surface. As the conversation gradually moves from technology and future exploration back toward human experience, something interesting tends to happen. Even after all the measurements, engineering advances, and careful scientific explanations, deep places like the Galathea Deep often still feel strangely personal. Not personal in the sense of ownership or direct familiarity, but in the way they provoke quiet reflection. Scientists themselves sometimes acknowledge this, though usually in understated language. The depth becomes not just a number or a data set, but a reminder of scale, limits, and perspective. Part of that reaction comes from how humans naturally interpret space. Most daily environments exist within manageable distances. Cities, landscapes, buildings, even mountains fall within a scale that can be navigated physically. The ocean trench, however, introduces a vertical dimension far beyond ordinary experience. Knowing something exists 10 kilometers below the surface, completely out of sight, triggers curiosity mixed with a subtle awareness of how little direct sensory access we actually have to much of our own planet. There is also the element of hiddenness. Space exploration often captures imagination because distant planets are visually accessible through telescopes. Deep ocean trenches remain concealed by water. No casual glance reveals them. That invisibility makes them feel more abstract, and abstraction often encourages imagination to fill in details. Scientists counter this tendency with data, yet the psychological effect persists even among professionals accustomed to interpreting numbers objectively. Researchers sometimes describe a gradual shift in perspective after repeated exposure to deep-sea data. Initial fascination with extreme conditions evolves into a quieter appreciation for complexity. Patterns in temperature, chemical composition, or biological adaptation begin to feel familiar. At the same time, awareness of remaining unknowns maintains humility. That balance between familiarity and uncertainty contributes to the personal dimension. Another factor involves time perception. deep ocean environments change slowly compared with many surface ecosystems. Sediment accumulation, tectonic movement, and biological adaptation often occur over decades or centuries. Studying such processes encourages long-term thinking. Scientists accustomed to faster laboratory cycles sometimes remark on how trench research subtly alters their sense of scientific timescale. Isolation contributes psychologically as well. Expeditions operating far from shore create a temporary separation from everyday routines. Even when research focuses strictly on data collection, the physical setting of open ocean tends to encourage reflection. Conversations aboard research vessels often extend beyond immediate technical concerns into broader discussions about environmental stewardship, scientific purpose, and global systems. Educational outreach reveals similar patterns among students. Learning about extreme environments sometimes prompts questions not only about science, but also about human place within natural systems. These reflections are not philosophical in an abstract sense. They arise directly from grappling with scale, complexity, and unfamiliar conditions. Cultural context influences perception too. Coastal societies often maintain long-standing relationships with the ocean through fishing, navigation, and folklore. Scientific descriptions of trenches add another layer to that relationship. Understanding depth scientifically can coexist with traditional perspectives, enriching both rather than replacing one with the other. Risk perception also shapes personal response. While scientists approach trenches analytically, awareness of extreme pressure, darkness, and cold still registers cognitively. This awareness does not translate into fear in professional settings, but it reinforces respect for environmental forces. That respect sometimes carries over into broader environmental awareness. Media portrayal occasionally amplifies emotional reactions. Documentaries highlighting deep-sea exploration can evoke awe or curiosity. Responsible communication aims to present balanced information, avoiding sensationalism while still conveying genuine scientific interest. The goal remains education rather than dramatic effect. Technological mediation again plays a role. Most people encounter the Galathea Deep through images, data visualizations, or narrated explanations rather than direct observation. This mediated experience encourages interpretation through imagination. Scientists work to ground interpretation in evidence while acknowledging that some level of personal reaction is natural. Long-term researchers sometimes develop attachment to specific study sites. Familiarity with data sets, seasonal patterns, and historical context fosters a sense of continuity. This attachment supports sustained commitment to monitoring programs essential for environmental science. Policy discussions occasionally incorporate this personal dimension indirectly. Public support for marine conservation often arises partly from emotional connection to ocean environments. Scientific communication that respects both factual accuracy and human response tends to be most effective. Educational curricula increasingly include ocean literacy components. Understanding deep environments contributes to broader environmental awareness. Students exposed to such material early often develop sustained interest in marine science. Interdisciplinary research acknowledges human perception explicitly. Psychologists studying environmental cognition sometimes collaborate with oceanographers to understand how people interpret extreme environments. These insights inform communication strategies. Climate awareness intersects here as well. Recognizing deep oceans as significant components of Earth's climate system reinforces understanding of planetary interconnectedness. This perspective encourages long-term thinking about environmental responsibility. Historical exploration narratives contribute cultural continuity. Stories of early expeditions, including those associated with the Galathea Deep, provide context for modern research. Continuity between past and present scientific efforts supports professional identity. Personal curiosity remains a powerful motivator. Many scientists trace career choices back to early encounters with ocean science. Deep environments often play a role in inspiring that curiosity. Public outreach programs sometimes include virtual dive experiences. Immersive simulations help audiences visualize depth, pressure, and darkness realistically. These experiences often generate reflective responses similar to those reported by researchers. Ethical considerations increasingly emphasize stewardship. Scientific understanding carries responsibility to minimize environmental impact. This principle resonates both professionally and personally among many researchers. Technological accessibility may expand public engagement further. Improved visualization tools, open access data, and interactive educational platforms allow broader participation in ocean science understanding. As this personal dimension settles alongside scientific knowledge, the Galathea Deep begins to feel less like a remote abstraction and more like part of a shared planetary system. That sense of connection supports ongoing curiosity without requiring dramatic interpretation, and with that quieter understanding in place, the discussion naturally begins easing toward a broader reflection on the overall journey through this topic, not as a final conclusion, but as a gentle continuation of thought about what deep ocean exploration reveals about science, perspective, and the steady unfolding of knowledge. As all these threads begin to settle together, the measurements, the biology, the engineering challenges, the geology, and even the human reactions to studying such places, what remains is not a dramatic revelation so much as a quiet awareness. The Galathea Deep, despite all the data collected over decades, still represents a part of Earth that operates largely outside everyday experience. Scientists know more now than when the first expeditions recorded its depth, yet knowledge has expanded outward rather than closing the subject. Each answer has tended to reveal additional layers of complexity rather than a simple endpoint. That pattern is actually quite typical in science. Discovery rarely eliminates mystery entirely. Instead, it refines it. Early explorers asked how deep the trench was. Later researchers asked what lived there. Then questions expanded toward chemical cycles, geological dynamics, ecological networks, and climate connections. Now the discussion includes technological innovation, environmental stewardship, and long-term monitoring. The subject keeps widening rather than narrowing. From a purely practical standpoint, deep trenches like this contribute quietly to global systems. They participate in carbon storage, influence ocean circulation, and record geological activity. These processes do not usually produce visible surface effects day to day, yet they remain part of the larger environmental balance. Understanding them supports climate science, hazard assessment, and biodiversity conservation efforts. The practical importance exists even when public attention shifts elsewhere. At the same time, there is something steady about how the ocean floor operates. Pressure, darkness, and cold create relatively stable conditions compared with many surface environments. Organisms adapt to those conditions gradually. Geological change occurs over extended timescales. That stability allows long-term scientific observation, though it also requires patience. Results accumulate slowly, often across multiple generations of researchers. Technological progress continues to shape what is possible. Instruments today can measure chemical traces, genetic material, and physical parameters with precision unimaginable to early expeditions. Autonomous vehicles extend observational reach. Data processing tools reveal patterns that once remained hidden. Future improvements will likely continue this trend, making sustained monitoring more routine rather than exceptional. Yet even with improved technology, direct human familiarity with these environments remains limited. Most understanding comes through mediation, instruments, models, remote imagery and analysis. That indirect relationship encourages certain professional humility. Scientists recognize that interpretation always involves some level of inference. Maintaining caution helps prevent overconfidence. Educational outreach reflects this evolving perspective. Instead of presenting deep trenches as purely exotic or extreme, many programs emphasize them as integral parts of Earth's system. This approach encourages balanced understanding. Curiosity remains, but it is paired with context and responsibility. Policy discussions increasingly consider deep-sea environments as well. Marine conservation frameworks, climate mitigation strategies, and resource management policies rely partly on data from abyssal regions. Scientific input helps ensure decisions rest on evidence rather than assumption. Continued research supports informed governance. Interdisciplinary collaboration appears likely to remain central. Oceanography now intersects with climate science, materials engineering, microbiology, data science, and even planetary exploration analog research. Trenches provide natural laboratories where multiple fields converge. This collaboration enriches interpretation while expanding research possibilities. Public perception sometimes oscillates between fascination and indifference regarding deep oceans. Media attention tends to spike around specific discoveries. Sustained awareness, however, depends more on education than occasional headlines. Communicating steady scientific progress helps maintain realistic expectations. Ethical considerations have grown more prominent over time. Earlier exploration emphasized discovery. Current approaches emphasize understanding combined with minimal environmental disturbance. This shift reflects broader environmental awareness and evolving scientific responsibility. Professional culture within oceanography reflects these changes. Younger researchers often enter the field already aware of conservation priorities, interdisciplinary collaboration, and technological integration. Training programs adapt accordingly. Long-term data continuity remains essential. Environmental processes unfold over decades or longer. Maintaining monitoring networks ensures future researchers inherit usable data sets. Institutional commitment to sustained observation supports cumulative understanding. Comparative study across trenches continue refining global models. Each trench contributes specific data points. Integrating them improves understanding of plate tectonics, deep ocean circulation, and biodiversity distribution. Technological accessibility may broaden participation in ocean science. Remote data platforms allow researchers worldwide to analyze data sets without physical expedition participation. This democratization of data supports broader collaboration. Cultural narratives about the ocean continue evolving. Traditional maritime knowledge, scientific research, and modern environmental awareness increasingly intersect. Respect for multiple perspectives enriches understanding. Looking quietly at the Galathea Deep now, after considering its depth, geology, biology, technology, and human perception, it appears less like a distant anomaly and more like one part of a vast interconnected planetary system. Its mystery has not disappeared, but it has become more structured. Unknowns remain, yet they are framed within expanding scientific context. And as this awareness settles gently rather than abruptly, The idea of the deep ocean often shifts from something distant or intimidating into something simply present, always there beneath the surface, influencing global systems steadily whether or not anyone is actively studying it at a given moment.